Every moment, the universe stretches farther into the unknown, expanding at an ever-increasing pace, keeping its deepest secrets hidden beneath the vastness of time and space. These secrets, ranging from the birth of galaxies to the mysteries of black holes and the possibility of life beyond Earth, continue to fuel humanity's relentless pursuit of knowledge. With every discovery, we learn more about our cosmic origins, revealing the ever-growing picture of what we understand and highlighting the enormous gaps that still await our exploration. As the universe expands, so too does the story of our existence, each step forward offering answers while raising new questions. The origin of the universe has intrigued scientists, philosophers, and thinkers for centuries. In their quest to unravel the enigma of how everything began, the most widely accepted explanation is the Big Bang Theory. This theory proposes that approximately 8 billion years ago, the universe originated from a singularity, an infinitely small, infinitely dense point, before expanding rapidly in an event unlike any explosion we typically understand. Rather than an explosion in space, it was a dramatic expansion of space itself. In those first moments, the temperature and density of the universe were so extreme that the environment was chaotic and filled with energy. The universe began as a swirling furnace of subatomic particles, each packed with unimaginable energy. As space stretched, the universe began to cool, allowing these particles to combine into the simplest forms of matter, atoms of hydrogen and helium. A few 100,000 years later, these atoms began to clump together, drawn by the force of gravity, eventually giving birth to the first stars and galaxies. The process of this cosmic coalescence laid the foundation for the intricate and expansive structure of the universe as we know it today, filled with stars, planets, and galaxies, all part of an ever-evolving cosmic tapestry. Yet, while the Big Bang Theory provides the broadest and most widely accepted narrative of the universe's beginnings, it does not answer every question or resolve every mystery. In fact, a number of alternative theories have emerged to address phenomena that the Big Bang model does not fully explain. One such theory is the concept of cosmic inflation. It suggests that immediately after the Big Bang, the universe underwent a rapid and exponential expansion in a fraction of a second. This period of inflationary growth accounts for why the universe, despite its large-scale homogeneity and isotropy, still exhibits a complex and clumpy structure at smaller scales. Cosmic inflation explains the uniform distribution of galaxies, radiation, and matter in the universe, solving a major puzzle about the large-scale smoothness of space. The rapid stretching of space during this inflationary period allowed regions of space that were previously far apart to become nearly identical, which, in turn, created the stable structures that we observe in the cosmos today. Without inflation, the universe would appear far more erratic, with more noticeable irregularities. The theory of cosmic inflation also raises intriguing possibilities about the multiverse, suggesting that our universe may not be alone in the vast expanse of existence. According to some models, our universe might be one of many, each existing in its own separate bubble, with each bubble potentially following its own distinct laws of physics. Another alternative, the cyclic model, proposes that the universe undergoes an endless cycle of birth, death, and rebirth, expanding and contracting over and over again, like a cosmic heartbeat. These cycles could stretch back into the infinite past, meaning that the Big Bang was not the beginning of everything, but rather one of many such events. This theory challenges our conventional understanding of time and origin, suggesting that the universe may have no ultimate beginning or end, but instead exists in a perpetual state of flux. Despite these alternative models, the Big Bang Theory remains the most dominant explanation for the origins of the universe. The evidence supporting it is compelling, and its implications are profound. One of the most persuasive pieces of evidence is the cosmic microwave background, CMB radiation, a faint glow that permeates the entire universe. This radiation is a relic from the early universe, providing a snapshot of what the cosmos looked like when it was just 300,000 years old. Detected in the mid-20th century, the CMB matches precisely what scientists would expect from a universe that began as hot and dense and gradually cooled over time. The uniformity and spectrum of the CMB align perfectly with the predictions made by the Big Bang model, confirming that the universe's early state was one of extreme energy and density, which later cooled to form the stars and galaxies we see today. In addition, the Big Bang theory also accounts for the distribution of light elements such as hydrogen and helium throughout the universe. During the first few minutes after the Big Bang, nuclear fusion occurred under conditions that were just right to form these fundamental building blocks. Observations show that about 75% of the universe is made up of hydrogen, while approximately 25% is helium, ratios that match the predictions of the Big Bang model. Another key piece of evidence for the Big Bang theory is the observation of the expansion of the universe itself. Astronomers like Edwin Hubble made the groundbreaking discovery that galaxies are moving away from us, with those farther away receding faster. This observation, known as Hubble's law, directly supports the idea that the universe has been expanding since the Big Bang and continues to stretch ever outward. Together, these various strands of evidence create a coherent and compelling narrative of a universe that evolved over billions of years, from a singularity of infinite density to the vast, complex cosmos we observe today. The story of the Big Bang is far from complete, though, and as we push further into the unknown, new discoveries will continue to refine our understanding, revealing even more layers of mystery and wonder hidden within the universe's grand design. Scientists employ a combination of observations and theories to determine the age of the universe, blending different methods that allow us to peer back in time and unravel the mysteries of our cosmic origins. Among the most significant of these approaches is the study of the cosmic microwave background radiation, or CMB, a faint, lingering afterglow of the Big Bang that still permeates the universe today. This ancient radiation, often described as the universe's first light, serves as a direct snapshot of the cosmos when it was just a few 100,000 years old. By studying the minute temperature fluctuations in the CMB, scientists can gather invaluable clues about the conditions that existed in the early universe. These fluctuations, though seemingly subtle, are rich with information about the universe's infancy and provide critical insights into its expansion. The CMB plays a central role in helping researchers measure the rate at which the universe is expanding, a key factor known as the Hubble constant. This constant, named after the astronomer Edwin Hubble, is essential for determining the universe's age. By precisely measuring these temperature fluctuations and using the Hubble constant to chart the expansion of the universe, cosmologists can trace backward in time and estimate that the universe is approximately 8 billion years old, a figure that has achieved widespread consensus across the scientific community. In addition to the study of the CMB, another primary method used to estimate the age of the universe involves observing distant celestial objects, particularly the oldest stars within our galaxy. Among the most useful stellar populations for this task are those found in globular clusters, dense groups of ancient stars that orbit the galactic core. By measuring the luminosity, temperature, and chemical composition of these stars, scientists can deduce how long they have been shining and estimate their age. Some of these stars are believed to be around 13 billion years old, establishing a lower limit on the age of the universe itself. If these stars have been burning for nearly as long as the universe has existed, it follows that the universe itself must be at least that old. The study of the expansion of space itself is also pivotal in our quest to determine the universe's age. Edwin Hubble's groundbreaking discovery that galaxies are receding from one another suggested that the universe has been expanding ever since the Big Bang. By measuring the velocities of these galaxies and the distances between them, scientists can create models that describe the rate of cosmic expansion. These models allow researchers to extrapolate backward, further refining our understanding of the universe's age. Through these calculations, the estimate has consistently been around 13.8 billion years, a figure that has become the standard for cosmologists. These different methods, studying the CMB, examining the oldest stars, and modeling the expansion of the universe, are cross-validated through various means, often involving data from space-based telescopes. For example, missions like the European Space Agency's Planck satellite have provided critical observations of the CMB, allowing for increasingly precise measurements. The alignment of findings from different approaches not only strengthens the validity of these estimates, but also continues to refine our understanding of the cosmos. As these methods converge, scientists inch closer to a more complete picture of the universe's history, piecing together the intricate story of how it evolved from a singularity into the vast, complex structure we observe today. The cosmic microwave background radiation is a powerful tool in this narrative. Its discovery was a turning point in the understanding of the universe, providing a relic of the very early cosmos, an invaluable time capsule that gives us a direct glimpse into the universe's nascent moments. The CMB is a faint glow that fills the entire universe, but what makes it so significant is that it is remarkably uniform. This uniformity suggests that the early universe was in a relatively smooth state, with small fluctuations in temperature that later gave rise to the galaxies, stars, and large-scale structures we see today. The importance of these temperature fluctuations cannot be overstated. They are key to understanding the distribution of matter in the early universe and how it eventually led to the formation of galaxies. By analyzing the CMB's temperature data, scientists can reconstruct the history of the universe's formation and uncover the forces that shaped it. These fluctuations in the radiation are also crucial for measuring other parameters of the universe, such as its age, composition, and rate of expansion. Crucial contributions from various missions, including the Wilkinson Microwave Anisotropy Probe WMAP and the Planck satellite, have provided essential data for determining that the universe is roughly 8 billion years old and consists largely of dark energy and dark matter. This discovery has profound implications for our understanding of the universe's evolution and future. The CMB serves as a cosmic relic, a tangible, measurable record of the universe's beginnings. It offers an extraordinary glimpse into the very moment that the universe transitioned from a hot, dense, and opaque state to the vast and expanding cosmos that we can observe today. Technological advancements over the past several decades have been crucial in transforming the study of the early universe from speculative theory into a well-established science. The development of powerful telescopes and detectors has been at the forefront of this transformation. Instruments like the Hubble Space Telescope have revolutionized our ability to observe distant galaxies, allowing scientists to study the formation of cosmic structures and the birth of galaxies over billions of years. These telescopes capture light that has traveled vast distances, providing invaluable data that enables researchers to trace the evolution of the universe. Furthermore, the rise of computer simulations has played an indispensable role in advancing our understanding of the early universe. With the increase in computational power, scientists can now simulate conditions that existed shortly after the Big Bang, phenomena that would otherwise remain elusive. These simulations help scientists explore the dynamics of matter and energy, from the formation of the first atoms to the birth of the first stars and galaxies. They also provide a platform for testing and refining theoretical models, such as the theory of inflation, which proposes that the universe underwent an incredibly rapid expansion just moments after its inception. Through these technological breakthroughs, we have made tremendous strides in our understanding of the universe. What once seemed like speculative hypotheses are now grounded in observational data and sophisticated simulations. The age of the universe, once a distant mystery, is now an established scientific fact, and every new discovery about its formation adds another layer to the intricate history of everything that exists. As scientists continue to refine their methods and tools, they bring us ever closer to a complete understanding of the universe's origins and its ultimate fate. Moreover, recent advancements in particle physics and detector technology have provided us with the ability to recreate conditions that closely resemble those found in the early universe. With facilities like the Large Hadron Collider, scientists are now able to probe the very essence of matter, investigating fundamental particles and forces that govern everything around us. By studying high-energy collisions, researchers gain valuable insights into the behavior of particles just moments after the Big Bang, drawing us ever closer to unraveling the profound mysteries of cosmic evolution. These experiments have become pivotal in our ongoing quest to understand not only the origins of the universe, but also the intricate processes that have shaped its development over billions of years. Another monumental breakthrough has been the advent of gravitational wave astronomy, which has opened entirely new dimensions in our understanding of the cosmos. By detecting ripples in spacetime caused by colossal cosmic events, such as the collision of black holes, scientists can now gain a fresh perspective on phenomena that have shaped the very fabric of the universe. These ripples offer us a view into previously hidden realms of the cosmos, shedding light on the most cataclysmic events that have occurred throughout cosmic history. These discoveries not only enhance our comprehension of the universe's past, but also illuminate the complex and delicate web of forces that continue to govern its evolution. In doing so, they reaffirm just how deeply technology has transformed our understanding of our origins. One of the most fascinating theories to emerge from this research is the concept of cosmic inflation. This theory describes a period of extremely rapid expansion of the universe that occurred just after the Big Bang. Picture the early universe as a tiny balloon, one that exploded outward at an astonishing rate. In less than a fraction of a second, around 1/1000th of a trillionth of a second, to be precise, the universe expanded from subatomic scales to vast cosmic proportions. This brief yet dramatic period of inflation solved numerous cosmological puzzles, including the uniformity of the universe and the formation of structures that we see today. The uniform temperature of the cosmic microwave background radiation, CMB, a faint glow that fills the universe and serves as a remnant of the Big Bang, is one of the most compelling pieces of evidence supporting the theory of cosmic inflation. This radiation appears remarkably uniform across vast distances, but inflation offers a profound explanation for this phenomenon. Regions that are now far apart were once in close proximity, allowing energy to equilibrate before rapid expansion pushed them apart. As a result, we observe a uniform temperature throughout the CMB, with slight fluctuations that eventually grew into the galaxies and clusters of galaxies we see today. Moreover, inflation offers critical insights into the formation of the universe's large-scale structure. Tiny quantum fluctuations present during this rapid expansion acted as seeds, which, under the influence of gravity, would eventually grow into the galaxies, stars, and clusters that populate the universe. These primordial fluctuations, through their interaction with gravity, set the stage for the complex and intricate structure of the universe as we know it. Thus, cosmic inflation serves as the bridge between the universe's earliest moments and the vast, interconnected cosmic systems we observe now. Understanding cosmic inflation reshapes how we view the universe, not just as an ever-expanding entity, but as one that began in an extremely uniform and hot state, gradually evolving into the vast, complex cosmos we see today. It challenges our perceptions and deepens our understanding of the origins of everything around us. Through this theory, we gain a clearer picture of how the universe transitioned from simplicity to the incredible complexity that now defines it, offering an entirely new perspective on the intricate dance of cosmic development. The universe is home to a vast array of galaxies, each possessing its own unique characteristics. Galaxies, the building blocks of the universe, come in many shapes and sizes, but they are generally classified into three primary types: spiral, elliptical, and irregular. Each galaxy type displays distinct features, shaped by the history of its formation and the gravitational forces that have shaped its evolution. Spiral galaxies, like our own Milky Way, are characterized by their stunning, winding arms that spiral out from a central bulge. These arms are populated with stars, gas, and dust, giving them a vibrant and dynamic appearance. The spiral structure is maintained through the rotation of the galaxy, as well as the influence of dark matter, which surrounds the galaxy and helps keep its shape intact over billions of years. Additionally, these galaxies are often regions of active star formation, with young blue stars lighting up the arms of the spiral. Elliptical galaxies, by contrast, differ significantly in appearance. These galaxies tend to be more spherical or oval, lacking the distinct arms found in spirals. Instead, they are typically older, containing mostly older stars and little to no star formation. Their smooth, featureless appearance is a result of their aging population of stars and a relative absence of the gas and dust needed to fuel new stellar births. Irregular galaxies, as the name suggests, do not fit neatly into either of the other two categories. Their structure is chaotic, and they are often rich in gas and dust, materials that are essential for vigorous star formation. Many irregular galaxies are the result of gravitational interactions or even collisions between galaxies, which disrupt their structure and lead to the creation of new stars. These galaxies offer a unique and dynamic window into the ongoing processes that shape the universe and its evolution. As time passes, clouds of gas and dust in the universe cool and condense, creating new stars and stellar systems. Many of these stars form in clusters, and as they interact gravitationally, they influence the surrounding material. Over time, this interaction leads to the development of more structured galaxies. The Milky Way, for example, can be described as a flat disk with a central bulge, spiral arms, and a surrounding halo. The central bulge is home to older stars and a supermassive black hole at its core, which plays a critical role in maintaining the galaxy's mass and structure. Surrounding the central bulge, the flat disk contains the majority of the Milky Way's stars, arranged in beautiful spiral patterns. These arms are the sites of active star formation, where gas clouds collapse to form new stars. The outermost region, the Milky Way's halo, extends far beyond the disk and bulge, containing older stars, globular clusters, and mysterious dark matter. Dark matter, which makes up a significant portion of the galaxy's mass, does not emit light, yet its gravitational influence is essential for keeping the galaxy intact. Despite its mysterious nature, dark matter plays an indispensable role in understanding how galaxies like the Milky Way function and hold together. Understanding the formation and structure of the Milky Way is crucial not only for exploring our own cosmic neighborhood, but also for gaining a broader understanding of the universe at large. It opens up critical questions about the origin of galaxies and the forces that have shaped the cosmos, revealing that our galaxy is part of a much larger and more intricate cosmic tapestry. The story of the Milky Way is a tale of cosmic evolution, one that is marked by the birth and death of stars, all woven together in a magnificent display of astronomical beauty. The Milky Way itself is thought to have formed about 13.6 billion years ago, shortly after the Big Bang. As matter began to clump together due to gravity, the first stars ignited, playing a pivotal role in shaping the galaxy. This process would continue over billions of years, resulting in the galaxy we inhabit today. However, the Milky Way is not alone in our corner of the universe. The Andromeda galaxy, known scientifically as M31, holds a special place in our cosmic neighborhood. Located about 2.5 million light-years away, Andromeda is the closest spiral galaxy to the Milky Way and serves as an important point of interest for astronomers. The two galaxies, both massive collections of stars and interstellar material, are on a collision course. In a few billion years, they will collide and eventually merge, likely forming a new, even larger galaxy. This event, often referred to as the Milkometa merger, presents an exciting opportunity to study the dynamics of galactic evolution and the processes that govern star formation. As the two galaxies collide, their structures will be reshaped, and their interactions will likely trigger bursts of new star formation as gas clouds collide and collapse under the influence of gravity. This impending merger will not only reshape the two galaxies, but will also offer astronomers invaluable insights into the forces that drive the evolution of galaxies. Through the study of such cosmic events, we continue to deepen our understanding of the universe, ever closer to comprehending the forces that have shaped and will continue to shape the cosmos for eons to come. Studying the Andromeda galaxy offers an unparalleled opportunity to peer into the deeper layers of cosmic history, shedding light on the formation, behavior, and evolution of galaxies that mirror our own. By examining Andromeda's structure, composition, and motion, scientists can draw essential comparisons between it and the Milky Way, advancing our understanding of how galaxies evolve over vast stretches of cosmic time. This neighbor, one of the most prominent and closest spiral galaxies to the Milky Way, is a celestial laboratory of sorts. It not only helps us understand the forces at play in our own galaxy, but also offers clues into the broader mechanics of the universe. Andromeda is an enormous galaxy containing approximately 1 trillion stars, vastly outnumbering the 200 billion stars in our own Milky Way. This stark contrast in size raises numerous questions for scientists. What drives this discrepancy in star density and distribution? What does this tell us about the potential for habitable systems within Andromeda? As researchers continue to scrutinize Andromeda, they delve into the mystery of its formation, motion, and interaction with the Milky Way. The more we uncover, the clearer it becomes that Andromeda holds essential keys to understanding the broader workings of the universe. Beyond its sheer size, Andromeda's significance lies in its dynamic nature. The galaxy isn't just a passive object in space, it plays a pivotal role in the grand dance of cosmic evolution. Galaxies, immense systems composed of stars, gas, dust, and dark matter, are not isolated. They are bound by mutual gravitational attraction, which can draw them toward one another. As galaxies drift through the cosmos, guided by the unseen hand of dark matter, they can end up on a collision course. These interactions are slow, spanning millions to billions of years. When galaxies approach one another, their outer regions begin to interact, stretching out into long tidal tails, and their gravitational forces start to reshape their very structures. While this might sound like a catastrophic event, the reality is far less destructive. Despite the incredible distances between individual stars, most stars in a galaxy won't actually collide. However, the gas within galaxies can interact, causing massive bursts of star formation. As these gas clouds collide and compress, new stars are born in the chaos, adding to the universe's ever-growing collection of stellar bodies. The upcoming collision between the Milky Way and Andromeda, predicted to occur in about 4 billion years, will likely trigger an explosion of new star formation as these galactic gas clouds collide. But the impact of such galactic collisions extends far beyond just new stars. As two galaxies merge, their structures begin to change. The newly formed galaxy often settles into a more stable arrangement, frequently resulting in an elliptical galaxy, a shape that's less conducive to new star formation than its spiral predecessors. These galactic mergers also play a critical role in the growth of supermassive black holes. At the heart of these galaxies, supermassive black holes feed on the excess gas and stars available during the collision, growing larger and more powerful over time. The consequences of galaxy collisions ripple through the cosmos, influencing not just the galaxies involved, but the very fabric of the universe itself. These collisions contribute to the cosmic evolution, helping to shape the structure of the universe and the distribution of galaxies across vast distances. Each galactic collision tells its own unique story, one of transformation, adaptation, and the ongoing cycle of creation and destruction in the cosmos. In the grand tapestry of existence, these collisions are not anomalies, but essential movements in the universe's unceasing ballet. However, the story of cosmic evolution doesn't end with galaxy collisions. Dark matter and dark energy, two of the most mysterious and crucial elements in the universe, play a fundamental role in shaping the cosmos. Together, they account for nearly 95% of the universe's mass energy content, yet remain elusive, detectable only through their influence on visible matter. Dark matter, which makes up approximately 26% of the universe, is an invisible substance that doesn't emit, absorb, or reflect light. It interacts with regular matter primarily through gravity, and its presence can be inferred from the behavior of galaxies and galaxy clusters. Without dark matter, galaxies would simply fly apart. It acts as a cosmic glue, holding galaxies and galaxy clusters together. On the other hand, dark energy, which constitutes about 69% of the universe, has a very different and even more mysterious function. Discovered through the study of distant supernovae, dark energy is responsible for the accelerated expansion of the universe. While dark matter pulls matter together, dark energy pushes it apart, counteracting the force of gravity on the largest scales. This cosmic force is reshaping the future of the universe, and understanding it is one of the greatest challenges facing astronomers and cosmologists today. Together, dark matter and dark energy form the backbone of the universe. They guide the distribution of galaxies in the vast cosmic web, influencing the formation and behavior of galaxies. Yet, despite their dominance, they remain largely beyond our direct detection, with their properties challenging our current understanding of physics. As scientists continue to explore these enigmatic forces, they unlock deeper layers of knowledge about the universe and our place within it. These discoveries could revolutionize our understanding of everything, from galaxy formation to the ultimate fate of the universe itself. To uncover these cosmic truths, scientists rely on a powerful arsenal of tools, most notably telescopes. Given the vast distances separating us from other galaxies, light takes an incredibly long time to travel to Earth. This means that when astronomers observe a galaxy billions of light years away, they are effectively looking back in time, witnessing the early stages of galaxy formation and evolution. Telescopes, particularly those positioned in space, are crucial in this endeavor. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have revolutionized our ability to study distant galaxies. These advanced observatories capture not only visible light, but also infrared and ultraviolet radiation, expanding our ability to study the cosmos in unprecedented detail. The James Webb Space Telescope, in particular, is designed to observe the universe in the infrared spectrum, allowing scientists to peer into galaxies that are billions of years old. Many of these distant galaxies emit light that is redshifted, meaning their light has shifted toward the red end of the spectrum due to the expansion of the universe. This phenomenon provides valuable insights into the early universe, helping astronomers trace the origins of galaxies and the evolution of cosmic structures. As we continue to explore the universe's distant corners, each observation brings us closer to unraveling the mysteries of our galaxy's past, present, and future. The study of Andromeda, galaxy collisions, and the cosmic forces of dark matter and dark energy all play pivotal roles in shaping our understanding of the universe's grand narrative, a narrative that is still unfolding across the vast, unknown stretches of space. Moreover, astronomers gather a vast range of data by observing the universe across multiple wavelengths, allowing them to construct a much richer and more detailed picture of the cosmos. For example, infrared observations unveil hidden details about the birth and evolution of galaxies, allowing scientists to track their formation over billions of years. On the other hand, ultraviolet light reveals crucial insights into the rate of star formation and highlights the presence of young stars, which are essential to understanding a galaxy's life cycle. By comparing and analyzing these different sets of data, astronomers can begin to piece together a timeline that traces the development of galaxies. This timeline not only sheds light on the progression of galaxies over time, but also helps assess their structures and compositions, revealing how these cosmic giants evolve. Advances in computer modeling and simulations have added another layer to this investigation. These powerful computational tools enable scientists to recreate the conditions that led to the formation of galaxies in the first place. By merging observational data with theoretical models, researchers continue to refine our understanding of the universe, offering new insights into the cosmic processes that shape galaxies and their complex evolution. Through this blend of observation and theory, we are gradually piecing together the grand narrative of our universe, unveiling mysteries that have puzzled astronomers for centuries. Each new discovery brings us closer to understanding how galaxies, those vast cities of stars, come into being, grow, and interact, all while offering us a deeper appreciation of our place in the cosmos. The birth of a black hole marks one of the most extreme and enigmatic processes in the universe. These objects, defined by an intensely strong gravitational pull, have a force so powerful that not even light can escape from them. This phenomenon begins when a massive star, having exhausted its nuclear fuel, can no longer support itself against the relentless force of its own gravity. The star's core collapses under this pressure, condensing into an incredibly small and dense point known as a singularity, which is surrounded by an event horizon, the boundary beyond which nothing can return. The formation of black holes begins in the final stages of a massive star's life cycle. When a star with a mass exceeding about 20 times that of our Sun runs out of fuel, it enters a violent phase known as a supernova. This colossal explosion marks the death of the star, expelling its outer layers into space while the core succumbs to gravitational collapse. The core becomes so compressed that it forms a singularity, and thus a black hole is born. Interestingly, not all black holes arise from dying stars. Some may form when two neutron stars, remnants of previous supernovae, collide. When these ultra-dense objects spiral towards one another and merge, they can generate enough mass and gravity to form a black hole. The collision of neutron stars creates ripples in spacetime, detected as gravitational waves. These ripples are like cosmic fingerprints, revealing a glimpse into the most dramatic and energetic events in the universe. Today, astronomers classify several types of black holes, each distinct in size and formation. Stellar black holes, for instance, are several times more massive than our Sun, and they form when individual stars collapse at the end of their life cycle. Supermassive black holes, however, reside at the centers of galaxies, with masses equivalent to millions or even billions of suns. These behemoths play a key role in the dynamics of their host galaxies, influencing their formation and evolution. The mysteries surrounding black holes captivate both scientists and amateur enthusiasts alike. They challenge our understanding of the fundamental laws of physics and continue to push the boundaries of our knowledge about the nature of reality itself. Black holes are extreme objects exerting immense gravitational forces that warp the very fabric of space and time. At the heart of this phenomenon lies a concept first proposed by Albert Einstein in his theory of general relativity, which describes gravity not as a force, but as a distortion or curvature of space-time. Imagine placing a heavy ball on a stretched rubber sheet. The ball creates a depression in the sheet, and any object placed near it will be pulled toward the ball. Similarly, when a massive star collapses into a black hole, it distorts the space around it, bending the very fabric of space-time. The region surrounding a black hole is called the event horizon. This is the point of no return. Once any object crosses this boundary, it is trapped forever by the black hole's gravity. One of the most mind-bending consequences of this distortion is the effect it has on time itself. As an object approaches the event horizon, time seems to slow down relative to observers far away. This phenomenon, known as time dilation, is one of the most fascinating consequences of the warping of space-time near a black hole. Time itself becomes malleable, stretching and bending in ways that defy our everyday understanding. Beyond their gravitational pull, black holes can also shape their surroundings in extraordinary ways. They often drive the accretion of gas and dust from their surroundings, creating incredibly hot and energetic disks of matter as it spirals inward. In the process, these disks emit intense radiation, which can be detected from vast distances. In some cases, black holes generate powerful jets of particles that shoot outward at nearly the speed of light. These jets can reshape the environments around them, potentially influencing the formation of stars and galaxies. The interplay between gravity, radiation, and matter creates a dynamic and energetic environment that continues to fascinate astrophysicists. The study of black holes provides us with a window into some of the universe's most extreme and mysterious phenomena. They challenge our perceptions of reality, forcing us to reconsider our understanding of gravity, space, and time. As scientists continue to observe and study these cosmic giants, they are not only learning about the black holes themselves, but also unveiling new insights into the fundamental laws that govern the universe. Each discovery brings us closer to understanding the complex and beautiful design of the cosmos. The concept of the event horizon is central to the study of black holes. This invisible boundary represents the point beyond which nothing, not even light, can escape the black hole's grasp. It is the ultimate edge of the known universe, where the normal laws of physics no longer apply. For astronomers, the event horizon is both a symbol of the limits of observation and a gateway to deeper understanding. As objects approach the event horizon, they experience intense tidal forces and warping of space-time. The gravitational pull near this boundary is so strong that it creates conditions unlike anything we can observe elsewhere in the universe. For scientists, the event horizon is not just a theoretical boundary, but a crucial aspect of understanding the nature of black holes. It is here, at the threshold of the event horizon, that the most profound mysteries of gravity and time unfold. As we continue to explore these strange and enigmatic regions of space, we are forced to confront the fundamental truths of the universe. truths that continue to challenge our deepest concepts of reality itself. The event horizon holds a critical place in understanding the mysterious nature of black holes, particularly when it comes to the controversial issue of information loss. As matter, whether it be gas or stars, plunges into a black hole, the information about their characteristics appears to vanish, as if swallowed by an impenetrable abyss. This scenario has sparked intense debates among physicists as it touches on some of the most profound and unresolved questions in modern physics. At the heart of the issue lies the conflict between two of the most well-established theories, quantum mechanics and general relativity. The struggle to reconcile these two pillars of science has led to a pursuit of a unified theory capable of explaining phenomena at both cosmic and quantum scales. The event horizon, however, is not merely a symbolic boundary. It marks a critical threshold, the point beyond which nothing, not even light, can escape. This line demarcates the region of no return for any matter that crosses it, trapping everything within. This boundary introduces deep challenges to our current understanding of physics, pushing the limits of what we know about the fabric of space and time. By studying this enigmatic feature, scientists are delving into some of the universe's most profound questions, from the nature of gravity to the strange relationship between information and reality itself. Black holes, by their very nature, are captivating. They are cosmic entities that emit no light, making them invisible to conventional observation methods. Despite this, astronomers have developed ingenious techniques to detect and study these mysterious objects. One of the primary methods involves observing the effects of black holes on their surroundings, particularly the motion of nearby stars and gas. When a star orbits a black hole, it follows a distinct path, revealing the presence of an unseen, massive object. By meticulously measuring this motion, astronomers can estimate the black hole's mass with remarkable precision. Another vital clue comes from the accretion disk that forms around a black hole. As matter spirals inward, it accelerates and heats up, emitting intense radiation, including X-rays. Telescopes like the Chandra X-ray Observatory are designed to detect these high-energy emissions. If a region of space emits significant X-rays without a visible star nearby, it often signals the presence of a black hole. These glowing regions of high-energy matter provide an indirect but powerful method for spotting the invisible giants that lie at the heart of many galaxies. Gravitational waves, ripples in the fabric of space-time caused by massive objects in motion, also offer an essential tool for studying black holes. When two black holes collide, they produce detectable waves that travel across the cosmos. Instruments like LIGO and Virgo have become pivotal in measuring these waves, giving scientists a unique opportunity to infer details about the black holes involved, including their mass and spin. This revolutionary technique has opened an entirely new avenue for understanding not just black holes, but the very structure of the universe itself. The discovery of gravitational waves marked a milestone in astrophysical research, offering a glimpse into the hidden workings of the universe. The ingenuity of scientists, constantly refining detection methods and pushing technological boundaries, has allowed us to uncover the secrets of these cosmic giants. By observing their gravitational effects, detecting high-energy emissions, and studying cosmic events like black hole mergers, researchers have pieced together a more complete picture of black holes. This ongoing quest continues to deepen our understanding of the universe's most enigmatic and powerful features, and as technology advances, we may yet unlock even more of their mysteries. Supermassive black holes, some of the most colossal objects in the universe, weigh millions to billions of times the mass of our sun. These behemoths reside at the centers of most galaxies, including our own Milky Way, and their formation remains a subject of intense investigation. Supermassive black holes grow by absorbing gas, dust, and even entire stars, and by merging with other black holes. Their gravitational pull is so immense that it exerts a profound influence over their galactic neighborhoods, shaping the structure and evolution of the galaxies that host them. Interestingly, the power generated by the material spiraling into a supermassive black hole can be breathtaking. As the matter accelerates and heats up, it often results in the creation of powerful jets of energy, as well as intense radiation that can illuminate vast portions of the cosmos. This energetic activity can have profound effects on the surrounding gas, often heating it to extreme temperatures and inducing powerful winds. These winds can disrupt the formation of new stars, influencing the life cycle of the galaxy. In many cases, the evolution of galaxies is inextricably linked to the behavior of the supermassive black holes at their cores, forming a kind of cosmic symbiosis. Recent studies have revealed a striking correlation between the mass of supermassive black holes and the properties of the galaxies they inhabit. Specifically, researchers have noted a connection between the mass of the black hole and the velocity of stars in the galactic center. This observation hints at a shared evolutionary path. When a supermassive black hole grows in size and becomes more active, it may simultaneously affect star formation rates and alter the stellar content of the entire galaxy. As a result, galaxies take on unique forms and behaviors, influenced by the unseen forces exerted by their central black holes. This emerging understanding is transforming how we view supermassive black holes. They are not simply cosmic monsters lurking in the depths of space. They are active players in the ongoing narrative of cosmic evolution, shaping not only the galaxies they reside in, but possibly even the structure of the universe itself. By refining our knowledge of these remarkable objects, we are gaining valuable insights into both the past and the future of galaxies, and perhaps even the fundamental dynamics of the universe. At the heart of every black hole lies its most mysterious feature, the singularity. This point, where gravity becomes so intense that space and time themselves are distorted beyond recognition, challenges the very foundations of physics. According to current theories, the singularity represents a region of infinite density, where the normal laws of physics break down completely. Everything that falls into a black hole is crushed into this infinitely dense point, creating a puzzle that scientists have yet to solve. Various theoretical models have been proposed to describe what might exist beyond the event horizon. One of the most prominent is the no-hair theorem, which posits that black holes can be completely described by just three properties: mass, electric charge, and angular momentum. According to this idea, all other information about the matter that once existed inside the black hole is lost, leaving only these three simple characteristics. If this theory holds true, black holes are more than just gravitational monsters. They may represent an ultimate erasure of information, turning complex cosmic phenomena into simple, seemingly inscrutable objects. However, some scientists propose that information might not be lost in black holes, but rather hidden in a complex and obscure manner. This idea challenges the traditional view that all information that falls into a black hole is irretrievably lost. One of the key figures in popularizing this concept is the renowned physicist Stephen Hawking, who introduced the revolutionary idea of Hawking radiation. According to this theory, black holes, instead of being impenetrable voids where information is destroyed, could gradually leak out information in the form of radiation. Over time, this radiation could lead to the black hole's gradual evaporation, suggesting that the information locked inside a black hole might eventually be released back into the universe. The implications of this theory are profound. If Hawking's radiation holds true, it would mean that information, rather than vanishing forever, is in some way preserved, albeit in a manner we don't yet fully understand. It also opens up the tantalizing possibility that information, once thought lost, might one day be recovered. However, this remains a contentious topic, with ongoing debates about how this information might be encoded in the radiation and whether it can truly be retrieved, or if it is irretrievably altered. Another fascinating and speculative theory revolves around the concept of wormholes. Some physicists suggest that black holes might not only be cosmic dead ends, but could also serve as gateways connecting different regions of the universe, or even separate universes altogether. These theoretical passages, known as wormholes, would allow for shortcuts through space-time, enabling faster-than-light travel or connections between distant corners of the cosmos. Though the idea of wormholes remains purely hypothetical, it captivates both the scientific community and the public, sparking imaginations and fueling numerous science fiction stories. While these theories remain speculative, they ignite curiosity and inspire further investigation. As our tools and understanding of the universe continue to develop, So too does the quest to uncover the secrets hidden within these cosmic enigmas. The mysteries of black holes, whether they be their information retention properties, their potential as portals to other realms, or their role in the larger structure of the universe, continue to challenge and inspire our pursuit of knowledge. In the grand tapestry of the cosmos, the life cycle of a star is a remarkable and transformative process. It begins in the heart of a molecular cloud, a vast region of space filled with gas and dust. Within these clouds, certain regions become denser and gravitationally unstable. Under their own weight, these dense pockets collapse, pulling in surrounding material. As this material accumulates, it forms a protostar, a dense, hot object that is the precursor to a full-fledged star. The gravity within the protostar pulls the surrounding gas and dust into a swirling, spinning disk. As the protostar's temperature rises, nuclear fusion begins to take place at its core, initiating the transformation into a main sequence star, a stage that marks the star's adulthood. For most stars, including our own Sun, this phase lasts billions of years. During this time, stars fuse hydrogen into helium at their core, a process that generates immense energy and light. The duration of this phase depends largely on the star's mass. Smaller stars like red dwarfs burn their hydrogen slowly and last for much longer, while larger stars consume their fuel more quickly and live comparatively short lives. Once a star exhausts its hydrogen fuel, its fate depends on its mass. For moderate mass stars, this marks the beginning of a dramatic transformation. These stars swell into red giants, their cores contracting while their outer layers expand. At this stage, helium begins to fuse into heavier elements. Once this process is complete, these stars shed their outer layers, leaving behind a dense core known as a white dwarf. The cooling and dimming of this white dwarf mark the final stages of a star's life. For massive stars, the end is even more cataclysmic. When a massive star runs out of fuel, it may explode in a supernova, a brilliant explosion that can outshine an entire galaxy. Depending on the remaining mass of the core, this explosion may leave behind a neutron star, a densely packed remnant where gravity is so strong that protons and electrons combine into neutrons, or it could collapse into a black hole, an object with gravity so intense that not even light can escape. This life cycle of stars is more than just a process of birth and death. It is a foundational mechanism that shapes the very fabric of the universe. From the collapse of gas clouds to the explosive death of massive stars, these processes form the building blocks for new stars, planets, and even life itself. As stars evolve, they not only create the elements that make up the world around us, but also enrich the interstellar medium, contributing essential materials for future generations of stars and planets. The mass of a star plays a dominant role in determining its lifespan and eventual fate. Larger stars burn through their nuclear fuel much faster than smaller ones. For example, a star with a mass several times greater than the Sun might burn through its hydrogen in just a few million years, while our Sun will continue to burn for roughly 10 billion years. This difference arises because larger stars have greater pressures and temperatures in their cores, which accelerates nuclear fusion processes. Smaller stars, like red dwarfs, burn their hydrogen slowly, allowing them to live much longer. In addition to mass, the composition of a star is also a crucial factor in its evolution. Stars are predominantly made up of hydrogen and helium, but the presence of heavier elements, known as metallicity, can significantly influence their development. Stars with higher metallicity are more likely to form dust and planetary systems, contributing to the creation of complex structures like planets and moons. These stars also generate heavier elements through their fusion processes, elements that are later spread throughout the cosmos when the stars die. Thus, the composition of a star plays a pivotal role in determining not just its evolutionary path, but also its ability to contribute to the cosmic ecosystem. As a star exhausts its nuclear fuel, it undergoes a series of dramatic transformations. For low to moderate mass stars, this culminates in the expansion into a red giant, followed by the shedding of outer layers to form a white dwarf. In contrast, massive stars experience a violent end, exploding in a supernova that can lead to the formation of a neutron star or black hole. These explosive events are not just the death throes of a star, they are essential for recycling matter. enriching the interstellar medium with the elements necessary for new stars, planets, and life to form. Measuring the size and composition of distant stars presents a fascinating challenge for astronomers. To determine a star's size, scientists use stellar parallax, a technique that involves observing the star from two different points in Earth's orbit around the Sun. The apparent shift in the star's position relative to more distant background stars allows astronomers to calculate its distance from Earth. With this distance known, other methods, such as analyzing the star's brightness and temperature, can be used to estimate its size. The luminosity of a star also plays a key role in determining its size. By using the inverse square law of light, scientists can calculate the distance to a star by measuring how much light reaches Earth. From there, they can compare the observed brightness to the intrinsic brightness of stars of similar type to estimate the star's size. A star that is particularly bright and large is likely to be a giant, radiating vast amounts of energy into space. To understand a star's composition, astronomers turn to spectroscopy, a technique that disperses light into a spectrum. Each element in a star absorbs and emits light at specific wavelengths, creating a unique spectral fingerprint. By studying these spectral lines, scientists can determine what elements are present in the star, as well as gain insights into its temperature, density, mass, and even its age. Through this detailed analysis, astronomers can peer into the heart of distant stars, unlocking the secrets of their composition and evolution. Advanced telescopes, including space-based observatories like the Hubble Space Telescope, have revolutionized our capacity to explore the cosmos, enabling astronomers to measure the size, age, and composition of distant stars with unprecedented precision. These powerful tools allow scientists to refine our understanding of the universe, unveiling a cosmic landscape where stars vary vastly in their characteristics. Each new discovery adds a crucial piece to the grand puzzle of our universe, revealing how stars evolve and how they shape the fabric of the cosmos. Through these ongoing efforts, astronomers are progressively peeling back the layers of mystery that have long surrounded the stars twinkling in our night sky. Among the most fascinating and enigmatic of these celestial objects are neutron stars, the final remnants of massive stars that exhausted their nuclear fuel and met their explosive end in a supernova. When a star of sufficient mass collapses under its own gravity, it compresses protons and electrons together, forming a dense core made up almost entirely of neutrons. This process results in a celestial body that is incredibly compact, with a mass greater than that of the Sun, yet only around 20 kilometers in diameter. The conditions within these neutron stars are extreme beyond imagination. To put their density into perspective, consider that a single teaspoon of neutron star material could weigh around 5 billion tons, an inconceivable mass packed into a tiny space. This remarkable density, combined with the sheer force of gravity at work, creates an environment where the laws of physics are pushed to their very limits. The study of such objects offers a unique window into the nature of matter under conditions that cannot be replicated here on Earth. Adding another layer of intrigue to neutron stars are pulsars, highly magnetized rotating neutron stars that emit beams of electromagnetic radiation. These beams are produced by the rapid rotation of the star combined with its strong magnetic fields. As the pulsar spins, its magnetic poles sweep through space, and if the beams are directed toward Earth, we witness a pulse of radiation with incredible precision. Some pulsars spin hundreds of times a second, making them among the most stable natural clocks in the universe. This extreme regularity is one of the reasons why pulsars are of particular interest to astronomers, who use their pulses to make critical measurements, such as calculating distances across the cosmos or detecting the subtle ripples in space-time caused by gravitational waves. The unique characteristics of neutron stars and pulsars offer invaluable insights into fundamental physics. Their extreme gravitational forces challenge our current understanding of particle interactions, space, and time itself. As these objects exist in such extreme environments, they allow scientists to probe the very fabric of the universe in ways that are otherwise impossible. One of the greatest mysteries that scientists aim to unravel is how matter behaves at such high densities. a puzzle that could reshape our knowledge of the universe's fundamental laws. But the significance of pulsars extends beyond just their role in helping us understand the physics of the cosmos. They also serve as vital tools for astronomers in their quest to measure the structure of the universe. By precisely timing the regular pulses emitted by these stars, scientists can map out vast stretches of space, measure cosmic distances, and even explore the ripples in space-time caused by the passage of gravitational waves. These observations have provided a wealth of knowledge, deepening our understanding of how stars evolve, how gravity functions across vast distances, and offering new insights into the life cycles of the very stars that light up our night sky. Moving from the singular wonders of neutron stars to the dynamics of multiple stars, binary star systems offer another intriguing facet of cosmic study. These systems consist of two stars orbiting a common center of gravity, bound together by their mutual gravitational pull. In some cases, these stars are in close proximity, while in others they may be separated by vast distances. The orbits of the stars can range from circular to elliptical, and in many cases the stars within these systems exert significant influence over one another's evolution, brightness, and even their eventual fate. The allure of binary systems lies in the wealth of information they provide about stellar evolution. By studying these stars in tandem, astronomers can gather critical data on their masses, sizes, temperatures, and luminosities, insights that are essential for understanding how stars form and evolve over time. One of the most significant factors in a star's life cycle is its mass, as it dictates how quickly a star will burn through its fuel and how long it will live. Larger stars, for example, burn their fuel much more rapidly than smaller stars, which can persist for billions of years. By studying binary systems, scientists can assess stellar masses with far greater accuracy than is possible with isolated stars. Additionally, binary star systems offer astronomers the opportunity to study other fascinating phenomena, including the discovery of exoplanets and the investigation of unique cosmic events. For instance, in eclipsing binary systems, where one star periodically passes in front of the other from our viewpoint on Earth, astronomers can observe changes in brightness that reveal crucial details about the size, composition, and dynamics of the stars involved. These systems also provide unique opportunities for studying the interaction between stars, such as when one star siphons material from its companion, leading to changes in their behavior and evolution. Through the study of both neutron stars and binary star systems, astronomers continue to unravel the complexities of the universe. Each discovery, whether it be the nature of pulsars, the extreme conditions of neutron stars, or the behavior of binary star systems, brings us closer to understanding the cosmic forces at play. The more we learn, the more we come to appreciate the intricate beauty of the universe and the awe-inspiring processes that govern the stars that illuminate the vastness of space. The mysteries of the stars remain ever compelling, and our pursuit of knowledge continues to deepen our connection with the cosmos. Furthermore, these stars exhibit some of the most fascinating and extreme behaviors in the universe. One such behavior occurs when a star enters its supernova phase, an event that is pivotal in the study of stellar death and the subsequent formation of neutron stars or black holes. This moment of destruction provides invaluable information about the end stages of a star's life. Supernovae are not just spectacular cosmic explosions. They are fundamental to understanding the very mechanics that govern our universe's evolution. The study of binary stars, systems in which two stars orbit one another, raises profound questions about the makeup of the cosmos. Among the most intriguing phenomena linked to these systems are gravitational waves. These ripples in spacetime are created when two neutron stars merge, and their detection has revolutionized our understanding of both the universe and fundamental physics. In these violent cosmic collisions, heavy elements like gold and platinum are formed, elements that are vital to the very structure of our own planet. These stellar mergers and their resulting gravitational waves offer a window into some of the most extreme and dynamic processes that shape the universe. As astronomers continue to explore binary star systems, they uncover deeper insights into the intricate relationships between celestial objects. These investigations reveal the complex processes that govern the life cycles of stars and the cosmic ballet they engage in, interactions that ultimately contribute to the structure and dynamics of the universe itself. Supernovae, in particular, hold a central role in this process. When a massive star nears the end of its life, it runs out of nuclear fuel, the source of its energy. Without this fuel to counterbalance the force of gravity, the star's core collapses. This collapse triggers an immense explosion, a supernova, which releases an extraordinary amount of energy. For a brief period, this explosion can outshine an entire galaxy. During this catastrophic event, heavy elements such as iron, nickel, and even heavier ones like gold and uranium are forged in the extreme conditions of the explosion. These newly formed elements are then ejected into space where they mix with interstellar matter, contributing to the formation of new stars, planets, and other celestial bodies. This process of cosmic recycling is fundamental to the continuing evolution of the universe. Supernovae, then, are not just destructive, they are also creative forces that help generate the building blocks for the next generation of cosmic objects. The shockwaves from these stellar explosions also have a significant impact on the dynamics of galaxies. As they propagate through space, they can compress nearby gas clouds, triggering the birth of new stars. This feedback mechanism influences the rate at which new stars form in galaxies, demonstrating that supernovae, while often seen as destructive events, also act as catalysts for new beginnings. Moreover, the study of supernovae provides key insights into the large-scale structure and evolution of the universe itself. By observing the light from distant supernovae, astronomers have been able to measure the acceleration of the universe's expansion. These observations led to one of the most profound discoveries in modern cosmology: the existence of dark energy, a mysterious force that drives the accelerated expansion of the universe. Thus, supernovae are not only crucial in the life cycle of stars, but also foundational to our understanding of the cosmos on the grandest scale. A planet, as we understand it, is a celestial object that holds certain defining characteristics. To be classified as a planet, an object must meet a few essential criteria. It must orbit a star, have enough mass to maintain a nearly round shape under its own gravity, and have cleared its orbit of other debris. This last criterion, the ability to clear its orbital neighborhood, is particularly significant as it highlights the planet's dominance in its region of space. However, this definition excludes bodies like Pluto, which no longer meet the full criteria and has since been reclassified as a dwarf planet. Within our solar system, the 8 recognized planets exhibit a stunning variety of characteristics, each shaped by its unique evolutionary history. These planets can be broadly divided into 2 categories: terrestrial planets and gas giants. The terrestrial planets, Mercury, Venus, Earth, and Mars, are rocky and have solid surfaces. They tend to be smaller in size and denser in composition compared to their gas giant counterparts. Earth, with its rich atmosphere and abundant liquid water, stands out as a rare and unique environment capable of supporting life. On the other hand, the gas giants, Jupiter and Saturn, as well as the ice giants, Uranus and Neptune, present a completely different set of characteristics. These planets are far larger and are primarily composed of gases and ices, lacking solid surfaces. Jupiter, the largest planet in the solar system, is a prime example of a gas giant. It boasts an immense atmosphere, dominated by swirling clouds and storms, including the iconic Great Red Spot, a colossal storm that has persisted for centuries. Saturn, famous for its beautiful rings, is another example of this category. The ice giants, Uranus and Neptune, while also gas giants, have distinct features. Their atmospheres are much colder, and their interiors are composed of heavier volatile substances such as water, ammonia, and methane, giving them a unique and frigid character. Uranus, in particular, rotates on its side, offering a glimpse into the extreme weather systems that can occur in distant corners of our solar system. The vast differences between the planets in our solar system create a rich and diverse tapestry of environments. These planetary bodies not only captivate scientists, but also inspire the imagination of people around the world. From the solid, life-supporting surfaces of Earth to the swirling storm clouds of Jupiter, the variety of planets provides an endless source of fascination and discovery, highlighting the complexity and wonder of the universe. As we continue to explore these celestial objects, we gain a deeper appreciation for the forces that shape them and the intricate processes that make the solar system and the cosmos at large so profoundly interconnected. From the boiling surface of Venus to the icy rings of Saturn, each planet in our solar system offers a unique perspective on the complex processes that shape planetary systems. These worlds, each with their own distinctive environments, serve as crucial windows into the formation and evolution of not only our solar neighborhood, but also the broader universe. By studying these diverse planets, scientists are uncovering the intricate factors that influence the development of planetary bodies, both within our system and far beyond it. This deepening understanding fuels humanity's relentless quest for knowledge, driving exploration and sparking new questions about the origins of the cosmos and the potential for life elsewhere. In recent years, the study of exoplanets, planets that orbit stars outside of our solar system, has emerged as one of the most thrilling frontiers in modern astronomy. With advances in technology, scientists now have the tools to identify these distant worlds with increasing precision. The methods employed to detect exoplanets are varied and sophisticated, each offering its own set of clues about these faraway planets and the environments they inhabit. One of the most powerful and widely used techniques for finding exoplanets is the transit method. This approach involves carefully monitoring the brightness of a star over time. When a planet passes in front of its host star, it causes a slight but noticeable dip in the star's light. This small but measurable change in brightness signals the presence of an exoplanet, and through this method, astronomers can also estimate the planet's size. Another key method is the radial velocity technique, often referred to as the Doppler method. This method relies on the star's light spectrum, looking for subtle shifts caused by the gravitational tug of an orbiting planet. As the planet orbits, its gravity causes the star to move slightly, leading to a shift in the light coming from the star, either toward the red end of the spectrum, redshift, or the blue end, blue shift. By studying these shifts, astronomers can confirm the presence of an exoplanet and calculate its mass, providing crucial information about its composition and the likelihood that it could support life. Telescopes equipped with cutting-edge technology, including space-based observatories like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, have played pivotal roles in revolutionizing our understanding of exoplanets. Kepler alone has discovered thousands of these distant worlds, each discovery expanding our knowledge of planetary systems scattered throughout our galaxy. These missions utilize highly sensitive instruments capable of detecting even the most minute changes in light and measuring a variety of stellar properties. Through these efforts, astronomers have been able to catalog a vast array of exoplanet types and sizes, ranging from gas giants that dwarf Jupiter to smaller, rocky planets that bear a closer resemblance to Earth. As our observational capabilities improve, so too does our understanding of these distant worlds. We are no longer just identifying exoplanets, we are also beginning to study their atmospheres and compositions. By analyzing how starlight filters through an exoplanet's atmosphere during a transit, scientists can detect the gases present and make inferences about whether the planet could support conditions favorable to life. This type of research is rapidly advancing, bringing us closer to answering one of the most profound questions of all: are we alone in the universe? Among the most exciting discoveries in the search for life beyond Earth are the exoplanets found in the habitable zones of their stars, regions where temperatures might be just right for liquid water to exist, a key ingredient for life as we know it. One notable example is Proxima Centauri b, which orbits Proxima Centauri, the closest star to our Sun, at just over 4 light-years away. This planet resides in its star's habitable zone, offering the tantalizing possibility of liquid water. Its proximity to Earth makes it a particularly intriguing target for future exploration. Another fascinating discovery is Kepler 186f, located about 511 light-years away. This exoplanet is approximately 1.5 times the size of Earth and orbits within the habitable zone of a faint red dwarf star. Its discovery was a landmark achievement as it marked the first time scientists found a planet about the size of Earth in a region where liquid water could potentially exist. Kepler 186f's position within its star's habitable zone raises the possibility that it may offer conditions similar to our own planet. Then there's the TRAPPIST-1 system, a remarkable star system just 40 light-years away that contains 7 Earth-sized planets, several of which are located in the habitable zone where conditions could allow liquid water to exist. The TRAPPIST-1 system has garnered considerable attention due to its potential for habitability. The planets in this system are particularly intriguing because they orbit a cooler star, which means they can orbit much closer to their star without being subjected to harmful radiation. This makes TRAPPIST-1 a prime candidate for further study in the search for life elsewhere in the universe. Finally, there is Gliese 581g, another exoplanet that resides in the habitable zone of its star. Although there is still some debate about its existence, Gliese 581g remains a subject of intense interest due to its Earth-like characteristics and potential for supporting life. Each of these exoplanets provides vital clues about what other worlds might be like and where, one day, we may discover evidence of life. As our exploration of distant planets continues, we are reminded that the universe is vast and full of possibilities waiting to be uncovered. While the search for life beyond our solar system remains one of humanity's greatest challenges, the discoveries of new exoplanets bring us ever closer to answering some of the most profound questions about our place in the cosmos. Within our own solar system, planetary atmospheres vary dramatically, shaped by a variety of factors such as the planet's distance from the Sun, its composition, and geological activity. For example, Earth's atmosphere is a delicate blend of nitrogen and oxygen, a mixture that has created the perfect conditions for life to thrive. In stark contrast, Venus has a thick atmosphere dominated by carbon dioxide with clouds of sulfuric acid. This creates a runaway greenhouse effect that raises surface temperatures to levels so high they could melt lead. Mars, on the other hand, offers yet another stark contrast. Its atmosphere is thin and mostly composed of carbon dioxide, with only trace amounts of other gases. This sparse atmosphere results in cold surface temperatures and a near-total absence of liquid water. Studying these extremes within our solar system helps scientists understand the diverse range of conditions that can exist on planetary bodies, furthering our understanding of what makes a world habitable. The solar system, a vast and intricate collection of celestial bodies, offers a fascinating glimpse into the dynamic nature of planetary atmospheres and the forces shaping the environments of worlds both near and far. Among these planets, Mars stands out with its unique and somewhat eerie landscape, shaped by the absence of a strong magnetic field. Over billions of years, the lack of this protective shield has allowed solar winds to strip away much of its atmosphere, leaving Mars with an environment that is not conducive to sustaining life as we know it. This phenomenon reveals how delicate a planet's atmospheric balance can be and how easily it can be disrupted by forces beyond its control. Looking further out into the solar system, gas giants like Jupiter and Saturn present a stark contrast to the rocky planets of Earth and Mars. These colossal worlds, primarily composed of hydrogen and helium, are not only massive but possess atmospheres that are in constant flux. The Great Red Spot on Jupiter, a storm so immense it could swallow Earth whole, exemplifies the incredible power and instability found in these gas giants. The atmospheres of these planets are thick with clouds, powerful storms, and high-speed winds, creating a chaotic yet stunning display of nature's forces. Saturn, with its iconic rings, is similarly dynamic, with its atmosphere exhibiting powerful winds and unpredictable weather patterns. Meanwhile, the ice giants Uranus and Neptune, while also composed of hydrogen and helium, differ significantly in their atmospheric behavior. These planets, shrouded in ice and dark blue clouds, reveal distinct weather systems, likely influenced by their unique internal heat sources and compositional differences from the gas giants. The ice giants remain mysterious and intriguing, offering a glimpse into the complex diversity of planetary atmospheres. As humanity's reach extends beyond our solar system, the discovery of exoplanets introduces even more diversity in atmospheric conditions. Some of these distant worlds orbit their stars at such close distances that their atmospheres are subjected to extreme temperatures, leading to the creation of vaporized atmospheres composed of exotic gases such as sodium and potassium. These planets challenge our understanding of atmospheric chemistry, offering new insights into the conditions that might exist on planets far from Earth. This exploration of exoplanetary atmospheres opens new frontiers in our understanding of the universe. It sheds light on the vast range of chemical, climatic, and atmospheric conditions that exist beyond our home planet. In particular, the discovery of water on other celestial bodies has profound implications for astrobiology and planetary science. Water, as we understand it, is essential for life, and its presence on other worlds raises tantalizing possibilities about the existence of extraterrestrial life. Scientists speculate that if life did emerge elsewhere in the universe, it would likely depend on water, which serves as a solvent for biochemical reactions vital to the survival of living organisms. Beyond its significance for the search for life, water also holds immense importance for human exploration. If humanity is to venture beyond Earth and establish permanent settlements on other planets or moons, access to water will be a critical resource. Not only will water be necessary for drinking and sanitation, but it can also be used to grow food. Moreover, water can be broken down into hydrogen and oxygen, which are key components of rocket fuel, making water-rich locations prime candidates for future exploration and habitation. Remarkable discoveries in the search for water have already been made. For example, scientists have confirmed the presence of ice on Mars, while beneath the icy surface of Europa, one of Jupiter's moons, vast oceans have been found. Further, telescopic observations have even detected traces of water vapor in the atmospheres of distant exoplanets, suggesting that water may be more widespread in the universe than previously thought. These discoveries provide exciting evidence that the conditions necessary for life may exist elsewhere in the cosmos, and they bolster the possibility of finding habitable environments beyond Earth. The importance of water in the search for extraterrestrial life and human exploration cannot be overstated. As we continue to uncover the mysteries of the universe, the discovery of water on other planets or moons will play a pivotal role in guiding our understanding of how life might exist elsewhere and how we might one day colonize distant worlds. This search is not only shaping our future, but also transforming our perspective on the universe, offering new avenues for exploration and discovery. In the grand scheme of our solar system, gas giants and rocky planets represent two fundamentally different categories of planets, each with unique features and characteristics. Gas giants such as Jupiter, Saturn, Uranus, and Neptune are dominated by thick atmospheres of hydrogen and helium. These planets lack a well-defined solid surface, which is why they are classified as gas giants. In contrast, rocky planets, also known as terrestrial planets, such as Mercury, Venus, Earth, and Mars, are made up of solid rocky surfaces composed of metals and silicate materials. One of the most striking differences between these two types of planets lies in their physical structure. Gas giants, with their enormous atmospheres, are home to thick clouds and intense storms. Jupiter's Great Red Spot, a storm that has persisted for centuries, serves as a testament to the fierce and ever-changing nature of these planets. The lack of a solid surface in gas giants means that their atmospheres dominate the planet's structure, creating an environment of swirling clouds and violent weather patterns. On the other hand, rocky planets like Earth have solid surfaces with a diverse array of geological features. From mountains to valleys and craters, these worlds are shaped by volcanic activity, tectonic movements, and erosion. Earth, with its dynamic tectonic plates, is the only planet in the solar system that supports life, a feature that sets it apart from its rocky counterparts. The presence of water and a breathable atmosphere on Earth is a crucial factor in the emergence and sustenance of life. The composition of these two types of planets also differs greatly. Gas giants typically have a small rocky core surrounded by an extensive atmosphere, which may include layers of liquid metallic hydrogen and icy layers. Rocky planets, in contrast, have a more uniform internal structure, with a dense metal core, a silicate mantle, and a solid crust where life can take root. This difference in internal structure gives rise to vastly different atmospheric conditions. For example, Venus's thick carbon dioxide atmosphere creates a runaway greenhouse effect, resulting in surface temperatures hot enough to melt lead. Earth, however, has a balanced atmosphere, rich in oxygen and nitrogen, that supports life. The formation of these two distinct types of planets also varies. Gas giants form in the colder regions of a protoplanetary disk, where they can accumulate vast amounts of gas. In contrast, rocky planets form in warmer regions, where solid materials can clump together to create a dense, rocky structure. This difference in formation processes plays a crucial role in the overall architecture of the solar system, and continues to be a subject of study for astronomers seeking to understand the origins of planetary systems. The story of our solar system's formation is a tale of cosmic evolution that began more than 4.5 billion years ago with a vast cloud of gas and dust known as the solar nebula. This nebula, primarily composed of hydrogen and helium, began to collapse under its own gravity, possibly triggered by shock waves from a nearby supernova. As the nebula contracted, it began to spin, flattening into a rotating disk. In the center of this disk, material gathered to form the Sun, and the intense heat and pressure of the forming star sparked thermonuclear fusion, giving birth to our Sun. Meanwhile, in the surrounding disk, particles collided and stuck together in a process known as accretion. These tiny planetesimals gradually grew larger through further collisions and gravitational interactions. Over time, these planetesimals coalesce to form the planets, moons, asteroids, and comets that now populate our solar system. One of the key theories explaining the current configuration of the solar system is the NICE model, which suggests that after the planets formed, they settled into stable orbits, shaped by the gravitational interactions between them. Through this incredible journey of planetary formation, the solar system became the complex and dynamic system we observe today. The study of these processes continues to inspire astronomers and scientists, offering clues about the potential for life on other worlds and the fundamental nature of planetary evolution. However, interactions between the giant outer planets, Jupiter, Saturn, Uranus, and Neptune, eventually led to a dramatic and massive rearrangement of our solar system. This model proposes that over millions of years, the planets migrated in their orbits, driven by gravitational forces. The shifting orbits of these colossal bodies likely caused Saturn and Jupiter to swap places, fundamentally altering the distribution of smaller bodies throughout the solar system. This migration had profound consequences, especially for the smaller rocky planets and the asteroid belt, shaping the present-day configuration of our celestial neighborhood. Another significant aspect of our solar system's current structure is the distinction between the inner rocky planets, Mercury, Venus, Earth, and Mars, and the outer gas giants. This division can be traced back to the solar nebula's temperature gradient, which influenced the formation of these distinct planetary types. The inner regions of the nebula, where the temperature was higher, allowed for the formation of rocky planets, while the cooler outer regions provided the ideal conditions for the development of gas giants. These massive planets gathered thick envelopes of gas and ice, forming the gas giants we know today. Together, these theories help explain not only how our solar system came into being, but also why it has taken its current form, filled with diverse worlds that continue to capture our imagination. The solar system is a complex and dynamic environment, constantly evolving as various forces interact with one another. Gravitational interactions are one of the primary drivers behind this ongoing change. The immense mass of the Sun exerts a gravitational pull that governs the orbits of the planets, moons, and smaller bodies like asteroids and comets. This gravitational influence causes the orbits of these celestial bodies to shift over time, leading to changes in their distance, speed, and occasionally even the potential for collisions. Beyond the gravitational forces of the Sun, celestial phenomena such as comets, meteoroids, and the asteroid belt also play crucial roles in the solar system's dynamic behavior. These smaller bodies can be nudged by gravitational forces, altering their orbits, and sometimes bringing them into the inner solar system. When these objects come close to the Sun, they can become active comets, displaying glowing tails as their icy components vaporize due to the Sun's heat. The potential for these bodies to collide with Earth is a reminder of the delicate balance that exists within the solar system. Impact events, though rare, can have significant consequences, including mass extinction events, such as the one that wiped out the dinosaurs. In addition to these phenomena, the solar cycle also contributes to the solar system's dynamism. Lasting approximately 11 years, this cycle sees fluctuations in solar radiation and magnetic activity. During periods of heightened solar activity, known as the solar maximum, the sun releases intense solar flares and coronal mass ejections. These energetic bursts of solar material can disrupt the space weather environment, affecting satellites, radio communications, and even power grids on Earth. These solar phenomena remind us that the sun's behavior directly impacts our daily lives, not just from a scientific standpoint, but also from a practical, real-world perspective. The gradual evolution of planets and moons due to geological processes adds yet another layer of dynamism to the solar system. Tectonic activity, volcanic eruptions, and erosion continue to reshape the surfaces of planets and their moons over millions of years. For example, Jupiter's moon Io is renowned for its extreme volcanic activity, driven by the tidal forces exerted by the planet's immense gravity. Similarly, Saturn's moons, such as Enceladus and Titan, are home to dynamic processes, including the eruption of water ice plumes and the presence of vast methane seas. These planetary bodies are not static. They are continuously evolving, giving us a glimpse into the ongoing processes that shape our universe. Comets and asteroids, as remnants from the early formation of the solar system, play an essential role in its ongoing evolution. These celestial bodies act as time capsules, preserving clues about the conditions and processes that led to the formation of our planetary system. Throughout history, the presence of these objects has raised both curiosity and fear due to their potential to collide with planets. These impacts have left their mark on Earth's evolutionary journey, often causing mass extinctions that paved the way for new species to emerge. Perhaps the most infamous example of such an event is the asteroid impact that occurred approximately 66 million years ago, leading to the extinction of the dinosaurs. The impact, which struck what is now the Yucatan Peninsula in Mexico, caused catastrophic climate changes, wiping out around 75% of all life on Earth. Yet, comets and asteroids have not only had destructive effects, they have also contributed to the development of life. When comets, composed mainly of ice and dust, collided with the young Earth, they may have delivered essential water and organic compounds, the building blocks of life. Scientific theories suggest that the early bombardment of Earth by these icy bodies provided the necessary elements for life to emerge, raising intriguing questions about the origins of life on Earth and whether other celestial bodies might harbor the potential for life as well. Beyond their impact on Earth's development, comets and asteroids also influence the gravitational interplay within the solar system. These objects can alter the orbits of other celestial bodies, affecting the stability of planets, moons, and smaller bodies. As a result, they play a vital role in shaping the long-term environment of our solar system. By studying the orbits and movements of these objects, astronomers can better understand the history of our solar system and predict potential future threats, including asteroid impacts that could have significant consequences for life on Earth. The search for Planet 9 has become one of the most tantalizing mysteries in modern astronomy. Although this hypothetical planet remains elusive, its existence is suggested by unusual gravitational effects observed in the outer solar system. Astronomers have noted that certain distant objects exhibit peculiar orbits that cannot be fully explained by the gravitational influence of known planets. This has led to the intriguing possibility that a massive, unseen planet might be lurking at the far reaches of the solar system. If Planet 9 does exist, it could be many times the mass of Earth and positioned far beyond Neptune, possibly taking between 10,000 and 20,000 years to complete a single orbit around the Sun. This mysterious planet could exert a gravitational tug on the smaller bodies in the outer solar system, shaping their orbits and potentially acting as an invisible shepherd for distant objects. Yet, despite the circumstantial evidence, no direct observations of Planet 9 have been made. Searches continue, and astronomers remain hopeful that this elusive planet will one day be discovered. The search for Planet 9 is only one part of the broader effort to understand the outer reaches of our solar system. The Kuiper Belt, a vast region filled with icy bodies beyond Neptune, may harbor additional undiscovered planets or celestial objects. As our technology and understanding of the cosmos continue to evolve, new discoveries are made regularly, pushing the boundaries of what we know about the solar system and the universe at large. Each new find adds to the growing body of knowledge about the dynamic forces at play in our celestial neighborhood, reminding us that the solar system is far from static and continues to reveal new mysteries. The mysteries of our solar system continue to captivate scientists and astronomers alike, driving an unrelenting quest for answers. Some theories even suggest that our solar system may have once harbored additional planets that were ejected due to gravitational interactions, their trajectories altered by the mighty forces of the gas giants. The pursuit of knowledge regarding such phenomena intensifies with each passing year, leading to groundbreaking discoveries. One of the most intriguing of these is the elusive Planet 9, a distant and potentially massive world whose gravitational pull might still be affecting objects at the outermost reaches of the solar system. Alongside it, a host of other potential companions could still be lurking in the shadows, fueling our fascination with the unexplored depths of our cosmic neighborhood. As we continue to search for answers, these mysteries remind us of the uncharted territory that remains, an unknown expanse that still drives our exploration of the universe. The Moon, Earth's lone natural satellite, holds a significant place in the story of our planet's evolution. Its influence has been profound, subtly shaping the course of life on Earth. One of the most important ways in which the Moon has affected Earth is by stabilizing the planet's axial tilt. This stability is crucial for the regulation of Earth's climate and seasons. Without the Moon, the planet's tilt could fluctuate much more dramatically, leading to extreme shifts in climate that could disrupt the delicate balance required to support life. Such instability would make it increasingly difficult for complex life forms to thrive, emphasizing the Moon's pivotal role in maintaining the environment that sustains us. The Moon's impact extends beyond the stabilization of Earth's tilt. It has also been instrumental in shaping the tides, one of the most visible and dynamic natural processes on Earth. The Moon's gravitational pull creates rhythmic rises and falls in ocean levels, known as tidal movements. These cycles have not only transformed coastlines over millions of years, but they've also fostered ecosystems, particularly in the intertidal zones. These zones, where land and sea meet, have become vibrant habitats teeming with diverse species of plants and animals, each uniquely adapted to the regular ebb and flow of the tides. The Moon's influence on tidal patterns has thus been a key factor in the development of life in these areas, providing a steady, reliable rhythm upon which many species depend. Throughout human history, the Moon has also had a profound cultural impact. Its phases have inspired myths, stories, and calendars, with many ancient civilizations venerating the Moon as a sacred entity. It was often linked to deities, serving as a symbol of mystery and power. The lunar cycle played a central role in marking time, guiding agricultural practices, religious rituals, and even navigation. This deep connection to the Moon reflects the extent to which its rhythms have been woven into the fabric of human existence, influencing everything from the structure of societies to the ways in which we measure time. The Moon also holds tremendous value for scientific exploration. By studying its geology, scientists have gained invaluable insights into the history of our solar system. The Moon's surface acts as a time capsule, preserving records of cosmic events that have remained largely unchanged for billions of years. This makes the Moon a crucial tool for understanding the early history of Earth itself, as it shares a deep connection with our planet's past. The exploration of the Moon, through both robotic missions and the eventual return of humans to its surface, will continue to unveil secrets that could reshape our understanding of both the Moon's origins and the story of life on Earth. Turning our gaze outward, the magnetospheres of gas giants like Jupiter and Saturn present a fascinating contrast to that of Earth. Unlike our planet, whose magnetic field is relatively small and stable, the magnetospheres of Jupiter and Saturn are vast, complex, and dynamic. Jupiter's magnetosphere is the largest in the entire solar system, extending millions of kilometers into space, far beyond the planet's atmosphere. This enormous magnetic field is generated by the planet's rapid rotation and its dense metallic hydrogen core. In comparison, Saturn's magnetosphere, while smaller, is still an extraordinary force, extending about 1.5 times the distance from Saturn to the Sun. Both of these planetary magnetic fields interact in dramatic ways with the solar wind, a constant stream of charged particles emitted by the Sun. The interaction between these powerful magnetospheres and the solar wind results in spectacular auroras at both Jupiter's and Saturn's poles. These auroras, much more intense than those on Earth, are created when charged particles are funneled into the planet's magnetic field lines, producing vivid glows that can be seen from space. Interestingly, these auroras change in intensity depending on the activity of the solar wind, offering scientists a glimpse into the dynamics of space weather. The moons of these gas giants, with their unique characteristics, play a crucial role in these phenomena. Jupiter's moon Io, for example, is one of the most volcanically active bodies in the solar system, constantly spewing material into space. This activity contributes to the formation of a plasma torus around Jupiter, intensifying its magnetic field. Saturn's moon Enceladus similarly ejects jets of water ice, which interact with the planet's magnetosphere and contribute to a complex ring of charged particles. The magnetospheres of Jupiter and Saturn are not just fascinating for their size and power, but also for the strange and energetic particles that reside within them. Researchers have identified energetic electrons, protons, and even heavier ions swirling in these magnetic fields. The study of these particles provides valuable insights into planetary atmospheres and space weather, allowing us to better understand the processes that govern not only these distant worlds, but also the broader nature of magnetism itself. Investigating the magnetospheres of these gas giants enhances our understanding of planetary science, offering lessons that extend well beyond the confines of our own Earth. Albert Einstein's theory of general relativity revolutionized our understanding of the cosmos, offering a new framework for comprehending the relationship between time and space. Prior to Einstein, the prevailing view of gravity was that it was a force acting at a distance, but Einstein proposed a radical new idea. Gravity is the result of massive objects bending the fabric of space-time itself. This insight changed the way we think about the universe, showing that time and space are not separate, static entities, but are intertwined in a dynamic, malleable fabric. One of the most profound consequences of general relativity is the phenomenon of time dilation. Time does not pass at a constant rate across the universe. Instead, it is affected by the presence of mass and gravity. For instance, time passes slightly slower near a massive object, such as a planet, compared to a location far from any gravitational influence. This effect, although imperceptible in everyday life, becomes more noticeable when objects move at extremely high speeds or are in close proximity to massive bodies. Einstein's famous thought experiment involving twins illustrates this concept perfectly. Imagine one twin travels at nearly the speed of light while the other remains on Earth. Upon the traveling twins' return, they would find that they had aged significantly less than their earthbound sibling. This surprising result is a direct consequence of time dilation, and it highlights the deep connection between time and the fabric of space itself. It serves as a reminder of how much there is still to learn about the nature of the universe and how interconnected the fundamental forces of the cosmos truly are. Einstein's groundbreaking theory of general relativity opened a door to a radically different understanding of the universe, suggesting that space and time are not static backdrops to events, but are dynamic, interconnected elements of a larger cosmic dance. It is within this framework that phenomena such as black holes come into focus, regions in space where gravity is so intense that nothing, not even light, can escape. These mysterious voids, which continue to challenge our understanding of the cosmos, raise profound questions about the fate of matter and information. According to general relativity, once something crosses the event horizon, the boundary marking the point of no return, its fate is sealed and it is pulled inexorably toward the singularity at the center. These concepts force us to confront the limitations of our knowledge, as they suggest that our current understanding of physics may no longer hold true under such extreme conditions. As we peer deeper into the vast expanse of space, the consequences of Einstein's theory become ever more practical. Technologies that are integral to our daily lives, such as GPS, depend on this new understanding of the universe. GPS systems require minute adjustments for time dilation, a phenomenon that occurs because of the gravitational influence of Earth on the passage of time. Without this correction, our ability to navigate the planet would be far less accurate. Einstein's theory has thus not only reshaped our conceptual view of time and space, but has also had tangible, real-world applications that continue to impact modern technology. Meanwhile, quantum mechanics explores a different realm of reality, one that operates at scales far smaller than what we experience in our daily lives. It describes the behavior of matter and energy at the atomic and subatomic levels, revealing a world that is anything but intuitive. In the quantum realm, particles can exist in multiple states simultaneously, a phenomenon known as superposition. Similarly, quantum entanglement reveals the extraordinary ability of particles to become linked across vast distances, with the state of one particle instantly influencing the state of another, regardless of the space between them. These behaviors defy our classical understanding of physics, suggesting that the universe operates on principles far more complex than our everyday experiences might suggest. In astrophysics, quantum mechanics provides vital insights into phenomena that occur in the high-energy environments far beyond our planet. Stars, including our own sun, derive their energy from nuclear fusion, an extremely complex process governed by quantum principles. In the cores of stars, hydrogen nuclei collide and fuse to form helium, releasing vast amounts of energy in the process. Quantum tunneling, a concept wherein particles can pass through barriers they would not normally be able to surmount, plays a pivotal role in making this fusion possible. This process, which occurs at the incredibly high temperatures and pressures found in the cores of stars, is a direct result of quantum mechanical effects. Quantum mechanics also plays a crucial role in understanding black holes and the behavior of light in intense gravitational fields. The way light interacts with matter under these extreme conditions leads to various phenomena, such as Hawking radiation. Proposed by the physicist Stephen Hawking, this theory suggests that black holes are not entirely black, but can emit radiation due to quantum effects near their event horizons. This idea fundamentally challenges the traditional view of black holes as completely dark and introduces a fascinating connection between quantum mechanics and gravity. In this way, quantum mechanics is pushing us to reconsider how we think about matter and energy, prompting us to expand our view of the universe. The intersection of quantum mechanics and astrophysics opens the door to exploring even deeper questions about the nature of reality itself. These include questions about the fabric of space and time, the origins of the universe, and the search for a unified theory that brings together general relativity and quantum mechanics. Theoretical models such as string theory and loop quantum gravity are at the forefront of this pursuit, offering potential frameworks for understanding the fundamental forces of nature. As scientists continue to probe these mysteries, quantum mechanics remains a cornerstone for understanding not only the smallest particles, but also the grand tapestry of the cosmos. String theory represents one of the boldest attempts to unify the various branches of physics. Unlike traditional physics, which posits that the universe is made up of point-like particles, string theory proposes that the most fundamental building blocks of the universe are tiny, vibrating strings. These strings vibrate in different ways, and it is through their oscillations that particles manifest, each corresponding to a specific vibrational pattern. This elegant framework offers the tantalizing possibility of a theory of everything, one that could unite general relativity, which governs the force of gravity, with quantum mechanics, which rules the behavior of particles at the smallest scales. A particularly striking aspect of string theory is its requirement for additional dimensions beyond the familiar four: 3 spatial dimensions and 1 of time. In its simplest form, string theory suggests that there could be as many as 10 or 11 dimensions. These extra dimensions, theorized to be compact and curled up in ways that are imperceptible to us, provide the theoretical foundation for reconciling the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. However, string theory faces significant challenges in terms of experimental verification. The scales at which string theory operates are far beyond our current technological capabilities, making direct observation or testing exceedingly difficult. While string theory has garnered considerable mathematical support, the lack of empirical evidence has fueled ongoing debates about its scientific validity. Despite these challenges, string theory continues to inspire a wealth of research, offering intriguing possibilities for the future. As scientists continue to explore its implications, they are not only seeking theoretical coherence, but are also investigating potential practical applications. The theory invites us to reconsider the very nature of reality, pushing the boundaries of human understanding and challenging us to think beyond the limits of the observable universe. Parallel to the exploration of string theory, the concept of the multiverse emerges as a fascinating proposition in cosmology. The multiverse theory suggests that there may be not one, but multiple, perhaps infinite, universes beyond our own. These universes could operate under different physical laws, constants, and even dimensions. Imagine, if you will, a vast cosmic landscape where every possible outcome of every event spawns a new universe, each one a unique manifestation of reality. This concept challenges the very nature of existence, suggesting that what we perceive as our entire universe could merely be a tiny fraction of a far larger and more complex web of parallel realities. One of the primary hypotheses supporting the multiverse theory arises from inflationary cosmology. Inflation refers to a brief period immediately following the Big Bang when the universe expanded exponentially in a fraction of a second. Some models of inflation suggest that this process did not occur uniformly, but rather in patches, creating bubbles or regions, each evolving into its own distinct universe. This means that our universe, with its unique properties, could be just one bubble in a vast, ever-expanding sea of universes, each with its own distinct set of characteristics. Quantum mechanics, with its concept of superposition, offers further support for the multiverse. In superposition, particles can exist in multiple states simultaneously, and only when observed do they collapse into a single outcome. This gives rise to the many worlds interpretation, which suggests that every possible outcome of every quantum event occurs in a separate branching universe. This idea implies that every decision, every action, every possibility spawns an alternate reality where a different outcome occurs. While direct evidence for the multiverse remains elusive, the intriguing possibilities suggested by string theory provide a theoretical framework in which multiple universes could exist based on the arrangement of extra dimensions. As research into string theory and the multiverse continues, these ideas remain some of the most mind-bending possibilities in our quest to understand the cosmos. But perhaps the most thrilling and enigmatic concept emerging from the realm of theoretical physics is that of wormholes. Often described as shortcuts through the fabric of space-time, wormholes offer the tantalizing possibility of rapid travel across vast distances, or even across time itself. According to the equations of general relativity, space-time can be thought of as a flexible, malleable entity. Picture it as a two-dimensional sheet of rubber. If you could bend the sheet and create a tunnel connecting two distant points, you would have a rudimentary visual representation of a wormhole. This idea has captured the imagination of scientists and science fiction enthusiasts alike, fueling countless stories and speculations about interstellar travel. In theory, a stable wormhole could provide a means of rapidly traversing galaxies or even traveling through time, enabling a spaceship to journey to distant stars in a fraction of the time it would take using conventional propulsion methods. However, while the concept is fascinating, there are significant hurdles to overcome before wormholes could become a reality. For one, they would likely require an enormous amount of negative energy to keep them open, a substance that, as of now, remains purely hypothetical. As we continue to push the boundaries of our understanding of the universe, the concepts of black holes, quantum mechanics, string theory, the multiverse, and wormholes serve as both a challenge and an invitation, a challenge to the limits of human knowledge and an invitation to explore the deepest mysteries of the cosmos. The more we uncover, the more we realize how much there is yet to discover. The concept of wormholes has long captured the imagination of scientists and science fiction enthusiasts alike. These hypothetical passages through space-time, which could potentially connect distant regions of the universe, promise the possibility of faster-than-light travel. However, the dream of traversing such cosmic shortcuts remains clouded by significant theoretical and practical hurdles. Despite the tantalizing potential, there are profound challenges that prevent wormholes from becoming a viable mode of transportation. For one, the geometry of a wormhole might be inherently unstable. It's possible that any wormhole, even if constructed, could collapse before a traveler could pass through it, annihilating the chance for interstellar travel. This instability stems from the extremely warped space-time curvature around the wormhole's entrance, which would create intense gravitational forces. These forces could pose deadly risks to anyone who attempts to pass through the wormhole, tearing apart both the traveler and the spacecraft. Yet, even with these concerns, the theoretical exploration of wormholes continues to push the limits of our understanding. The idea of such portals encourages a sense of wonder and curiosity, urging us to reconsider the fundamental structure of the universe itself. While practical use remains far beyond our current technological capabilities, the study of wormholes remains a crucial avenue for expanding our knowledge of space-time. If we can uncover their true properties, we might one day unlock revolutionary insights into how we perceive distance and perhaps even travel vast distances across the cosmos. Beyond the idea of wormholes, the nature of time itself poses another fascinating barrier to space exploration: time dilation. Rooted in Einstein's theory of relativity, this phenomenon tells us that time is not a constant, fixed experience for all observers. In fact, time behaves differently depending on how fast you're moving and how strong the gravitational field you're in is. As we set our sights on the stars, we are forced to grapple with the reality that time will pass differently for travelers in space compared to those on Earth. Consider astronauts traveling at speeds approaching the speed of light. For them, time would seem to slow down drastically compared to people on Earth. A journey that might take only a few years for the crew could result in decades or even centuries passing back home. This is a critical challenge for space exploration, particularly when we think about missions to distant star systems. If a spacecraft were to set out toward a distant star, say several light years away, time dilation would mean the astronauts aboard might experience only a couple of years of aging during their voyage. But for those left on Earth, decades would pass, and the planet would have changed significantly in the meantime. This discrepancy between the traveler's experience of time and that of those on Earth presents a host of complications. For one, it creates a major challenge for mission planning, especially when considering long-duration trips to the outer reaches of our galaxy. The potential for astronauts to return to an Earth that has moved on without them poses an unsettling reality. The changes in society, technology, and culture they might encounter could be staggering, and the emotional and psychological impacts on the astronauts themselves are just as profound. Importantly, time dilation isn't just a theoretical curiosity. It's something we've already observed. Experiments involving atomic clocks flown aboard high-speed jets have confirmed the effect, with clocks aboard the planes registering less time than those left on the ground. While these differences may seem tiny on a human scale, they provide concrete proof that time dilation is very real and measurable. As humanity continues to look toward the stars, we must also consider the implications of this phenomenon on communication. Space travelers sending messages back to Earth would find that their signals are delayed, not just because of the vast distances involved, but also because of the time dilation effects. The further a spacecraft ventures, the greater the lag in communication. This delay compounds the feeling of isolation that astronauts would inevitably experience, making the journey into deep space as much a psychological challenge as a physical one. Understanding time dilation, then, isn't just a matter of theory. It's essential for planning missions that aim to cross vast distances and connect with far-flung destinations. This exploration of time also ties into one of humanity's most profound quests: understanding the origins and potential for life beyond Earth. How did life begin on our planet, and could it arise elsewhere in the universe? Astrobiologists have proposed several theories to answer these questions, each with its own implications for the possibility of life beyond Earth. One of the leading theories is abiogenesis, which posits that life can emerge naturally from non-living matter. This process likely begins with the formation of simple organic molecules, such as amino acids, which can combine to form more complex structures, eventually leading to the emergence of cellular life. Environments rich in energy, like hydrothermal vents deep on the ocean floor or the shallow pools of early Earth, are thought to be ideal settings for these reactions to occur. Another intriguing possibility is panspermia. This theory suggests that life on Earth may not have originated here at all. Instead, life, or at least the building blocks for life, could have been brought to Earth by comets, meteorites, or cosmic dust. Recent discoveries of extremophiles, organisms that thrive in some of the most hostile environments on Earth, lend support to this idea. These organisms are capable of surviving extreme conditions, including those found in the vacuum of space, which raises the possibility that life, or at least its fundamental components, could endure the rigors of interstellar travel. In addition to these theories, scientists are also exploring the possibility of alternative biochemistries. While life on Earth is based on carbon and water, researchers speculate that other forms of life could rely on completely different elements or solvents. For example, some theorize that silicon-based life forms might exist, capable of thriving in environments far different from our own. The discovery of exoplanets in the habitable zones of distant stars has sparked renewed interest in these ideas. As we find more and more planets that could potentially support life, the imagination of scientists and the public alike is fired up. How diverse could life be out there? What forms could it take? Could life on these planets be so different from our own that it defies everything we understand about biology? These questions challenge the very nature of life and our place in the universe. As humanity ventures into the unknown, seeking answers to these mysteries, one thing is clear. We are on the cusp of exploring the most profound questions about existence itself. The exploration of wormholes, time dilation, and the origins of life beyond Earth are not merely theoretical exercises. They are key to understanding our place in the cosmos and perhaps the future of our species. The study of extreme environments on Earth has become a pivotal force in shaping our understanding of life's remarkable adaptability. From the freezing realms of Antarctica to the sulfur-rich pools of Yellowstone, life has proven time and again its ability to thrive in places that appear completely inhospitable to human survival. This adaptability, displayed by microorganisms, plants, and animals alike, raises profound questions about the nature of life itself. Could similar, extreme conditions elsewhere in the universe also support life forms? As we explore the boundaries of what constitutes a livable environment, these questions push the limits of our scientific knowledge, expanding the scope of where life might exist. The search for extraterrestrial life, an endeavor that has long captivated human curiosity, continues to evolve. It blends relentless curiosity with rigorous scientific inquiry, bringing us ever closer to answering one of humanity's most monumental questions: are we alone in the cosmos? Through the use of cutting-edge technologies and innovative methodologies, scientists are now probing distant worlds within our own solar system. Their efforts span across planets, moons, and even asteroids, targeting environments that might harbor life, past or present. At the heart of these explorations is the recognition that life, as we know it, depends on three fundamental components: water, energy, and organic compounds. The quest to find extraterrestrial life hinges on identifying locations that could provide these elements in a stable, sustainable way. One of the most promising destinations in this search is Mars. Robotic missions like NASA's Perseverance rover have been tirelessly analyzing the Martian surface and its underlying geology. These rovers are not only searching for signs of ancient microbial life, but also collecting soil samples that, in the future, may be brought back to Earth for more in-depth analysis. The key focus of these missions is areas where liquid water may have once flowed, regions where biological traces are more likely to have survived the test of time. But beyond Mars, the search has expanded to other corners of the solar system. Researchers are now turning their attention to the icy moons of Jupiter and Saturn, where the potential for life exists beneath frozen crusts. One of the most intriguing moons is Europa, a moon of Jupiter believed to harbor a vast ocean beneath its icy surface. This subsurface zone, kept warm by the moon's gravitational interactions with Jupiter, could provide a stable environment for life. Similarly, Enceladus, Saturn's sixth largest moon, has geysers that eject plumes of water vapor and organic molecules into space. Future missions are planned to sample these plumes, providing scientists with an invaluable opportunity to analyze the chemical makeup of these jets and, perhaps, uncover biological markers. The search for extraterrestrial life also extends to comets and asteroids, celestial bodies that could contain the essential building blocks of life or even evidence of past life. By studying these ancient objects, scientists hope to uncover vital clues about how life may have originated on Earth, and whether the same processes could occur elsewhere in the universe. These explorations are not just focused on finding life, they are equally concerned with understanding the conditions necessary for life to exist, which in turn broadens our perspective on the nature of the universe and our place within it. As we ponder the possibility of life beyond Earth, certain celestial bodies draw our attention because of their unique environments. Mars, for example, has long intrigued scientists due to compelling evidence suggesting that it once had a warmer and wetter climate. Features such as ancient river valleys, dried-up lake beds, and polar ice caps indicate that liquid water may have flowed freely on the surface in the distant past. Ongoing missions, such as those led by the Perseverance rover, continue to explore the Martian surface in hopes of uncovering microbial life or remnants of life from an ancient epoch. The prospect that Mars could once have supported life, even if only for a brief moment, fuels our excitement and curiosity about the planet. The moons of Jupiter and Saturn also represent some of the most tantalizing targets in the search for life. Europa, one of Jupiter's moons, is thought to possess an expansive ocean beneath its icy surface, a body of water that could have the right chemical composition and temperature to support life forms. The tidal forces exerted by Jupiter on Europa help maintain the warmth of this hidden ocean, making it one of the most promising locations in the search for extraterrestrial life. Similarly, Enceladus, a moon of Saturn, has demonstrated remarkable features, including geysers that shoot water and organic molecules into space. This evidence suggests that Enceladus's subsurface environment could also be conducive to life, particularly microbial life. While the focus of these explorations remains within our solar system, the search for extraterrestrial life is not limited to nearby worlds. Exoplanets, planets orbiting stars outside our solar system, are becoming key players in the ongoing quest. Among these exoplanets, those located in the habitable zone, sometimes referred to as the Goldilocks zone, are of particular interest. These are the regions around stars where conditions may be just right for liquid water to exist on a planet's surface. One such planet, Proxima Centauri b, located in the habitable zone of the closest star to our Sun, has captured the attention of scientists and astronomers alike. Advanced telescopes and other cutting-edge technologies are enabling astronomers to study the atmospheres of these distant worlds. By searching for biosignatures, such as the presence of oxygen or methane in the atmosphere, scientists hope to detect potential signs of life on these far-off planets. With each new discovery, whether it be from the Martian surface, the icy moons of Jupiter and Saturn, or distant exoplanets, the field of astrobiology, the study of life in the universe, continues to evolve. These discoveries add valuable pieces to the cosmic puzzle and bring us one step closer to understanding the true extent of life beyond our planet. Alongside the exploration of physical environments, the search for extraterrestrial intelligence, SETI, has been another key component of humanity's efforts to understand whether we are truly alone in the universe. SETI operates through an array of sophisticated, well-planned initiatives aimed at detecting electromagnetic signals from other civilizations. Using radio telescopes, scientists scan the cosmos for unusual signals that might stand out against the background noise of the universe. The basic idea behind SETI is simple. If intelligent life exists elsewhere, it may be sending messages into space, and we just need to listen. Radio frequencies, due to their ability to travel vast distances without significant interference, have been the primary focus of SETI research. One of the most well-known SETI programs involves large, powerful radio dishes that monitor specific stars exhibiting characteristics that suggest they might host planets capable of supporting life. By analyzing the data received from these signals, scientists hope to identify patterns or structures that could indicate an artificial origin as opposed to natural cosmic phenomena. In recent years, the power of technology has vastly improved, allowing for more sophisticated techniques in data analysis. Machine learning algorithms, for example, can now process enormous amounts of data in real time, enabling scientists to identify potential signals much faster than ever before. As our tools improve and our understanding deepens, the search for extraterrestrial life and intelligence continues to evolve, offering hope that one day we may finally answer the age-old question, are we alone in the universe? The journey, driven by curiosity and scientific rigor, is far from over, and with each step, we edge closer to uncovering the secrets of the cosmos. In the search for extraterrestrial life, the scientific community is expanding its approach in ways that were once unimaginable. Traditional methods of searching for signals through radio waves are now being supplemented with a groundbreaking new approach, laser communications. Researchers are developing optical SETI, search for extraterrestrial intelligence, programs that explore the possibility of laser signals being the key to interstellar communication. By looking beyond the familiar radio frequencies, these efforts are broadening the scope of the search for intelligent life in the universe, offering new hope in this long-standing quest. Public involvement has become a powerful force in SETI research, helping to accelerate progress and engage the broader population in the scientific journey. Initiatives like SETI at Home have revolutionized how we approach the search, allowing citizen scientists to contribute their computing power to analyze signals collected by radio telescopes. This democratization of science is not only speeding up the research process, but it also generates a collective sense of curiosity and excitement, inviting people from all corners of the world to participate in one of humanity's most ambitious undertakings. At its core, SETI represents a universal endeavor, humanity's effort to listen for the faintest echoes of intelligent beings scattered across the vastness of space. It asks profound questions about our place in the cosmic narrative. Could we be alone, or are we simply waiting for the right signal, the right moment, to bridge the immense distance between us and an unknown civilization? In our search for extraterrestrial life, we are simultaneously searching for meaning in the universe, or trying to understand how other civilizations, if they exist, might communicate, and perhaps how they might view us. One of the greatest challenges in establishing contact with extraterrestrial civilizations is communication itself. The methods and languages that alien species may use could be entirely beyond our comprehension. Human communication relies on a shared understanding of symbols, sounds, and gestures. But what if the beings we seek to connect with use forms of communication that don't resemble anything we know? What if their concept of language is completely foreign to us, built upon principles and perceptions so different that we wouldn't even recognize it as language? Distance is another daunting challenge. Space is not only vast, but time itself behaves differently when we send signals across it. For example, if we were to send a message to a planet located 10 light years away, it would take 10 years for the signal to reach its destination. Then, assuming a reply is sent, it would take another 10 years to return. This means that every exchange could take decades or even centuries, making any kind of meaningful real-time conversation virtually impossible. The time delay means that our transmissions could be nothing more than solitary echoes, drifting in the void with no guarantee that anyone is listening. In addition to the inherent delay, the signals themselves pose another issue. Our radio waves, or any other method of communication we currently use, may not even be detectable by alien civilizations. Our signals could be weak, lost in the cosmic background noise, or simply unrecognized by species with radically different technological advances. Even more concerning is the possibility that our messages may degrade over vast distances, making them unreadable to potential recipients, no matter how sophisticated their technology might be. If we hope to maintain communication across light years of space, ensuring that our messages can endure the harshness of space is crucial. Moreover, there's the question of how alien civilizations might perceive our messages. Given that we have no understanding of their cultural context or values, it's possible that our attempts at communication could be misinterpreted. What if they perceive our signals as a threat rather than an invitation? The potential for cultural misalignment could have profound implications for interstellar diplomacy, as misunderstandings may result in unintended consequences. The challenges of intent, perception, and interpretation will need to be carefully navigated as we pursue contact across the stars. As humanity grapples with these challenges, the field of astrobiology has gained increasing prominence. Astrobiology seeks to understand the conditions that allow life to thrive beyond Earth, exploring what makes certain environments hospitable to life and what might make other planets or moons suitable for life as we know it. A key focus within this field has been the study of extremophiles, organisms that can survive in conditions once thought to be hostile to life. From boiling hot springs to the frozen deserts of Antarctica, extremophiles have shown remarkable resilience in environments that challenge our understanding of biology. Some thrive in highly acidic lakes, while others endure the crushing pressures of the deep sea or the intense radiation of space. By studying these extraordinary organisms, scientists have come to realize that life, in its most basic form, may be far more adaptable than we ever imagined. This discovery has led to exciting possibilities for life on other planets and moons, especially those located in extreme conditions. One of the most promising areas of research in this field is the study of moons like Europa, one of Jupiter's largest satellites. Beneath its icy surface, scientists believe there exists a vast subsurface ocean, which could potentially harbor life forms capable of surviving in extreme environments. If life can thrive on Earth under such harsh conditions, it stands to reason that similar organisms could exist in the subsurface oceans of Europa or other moons within our solar system, expanding the potential locations where life might be found. The study of extremophiles is also revolutionizing how we search for life elsewhere in the universe. These hardy organisms offer new insights into how we might detect life on distant exoplanets. By understanding the mechanisms that allow extremophiles to survive in extreme conditions, scientists are developing innovative techniques for identifying life in similarly harsh environments on distant planets, moons, and beyond. These discoveries challenge traditional views of where life might be found and push the boundaries of what we consider to be habitable zones in the cosmos. The search for life, however, is not confined to Earth's extreme environments. Advances in space exploration, particularly the launch of space telescopes like Hubble and the James Webb Space Telescope, Webb, have greatly expanded our understanding of the cosmos. Launched in 1990, Hubble transformed our ability to observe distant galaxies, nebulae, and other celestial phenomena, offering a view of the universe that was once inaccessible. Free from the distortions caused by Earth's atmosphere, Hubble's clear view of the cosmos has allowed astronomers to uncover mysteries about the universe's expansion and evolution. One of the most groundbreaking discoveries from Hubble was the revelation that the universe is not only expanding, but that this expansion is accelerating. This has led to the theory of dark energy, a mysterious force that constitutes much of the universe but remains largely unexplained. Hubble's observations have reshaped our understanding of cosmic history, offering insight into how galaxies form, evolve, and interact with one another over billions of years. Its role in understanding the life cycle of stars, as well as the conditions necessary for life, has been instrumental in our ongoing quest to understand the universe. The James Webb Space Telescope represents the next step in this cosmic journey. Designed to observe the universe in infrared light, Webb can peer through cosmic dust clouds that often obscure our view of distant stars and planets. This capability opens new doors for studying the formation of planetary systems and the birth of stars, shedding light on the processes that shaped our solar system. Webb's most exciting mission, however, may be its ability to study exoplanets, planets orbiting stars outside our solar system. By analyzing the atmospheres of these distant worlds, Webb could potentially detect key elements such as water vapor, carbon dioxide, and other substances essential for life. This data will help scientists answer some of the most profound questions about the prevalence of life beyond Earth. The answers Webb uncovers may bring us closer than ever to understanding the true scale of life in the cosmos, reshaping our view of the universe in ways we are only beginning to imagine. Through the continued exploration of space, the study of extremophiles, and the innovative technologies offered by telescopes like Hubble and Webb, humanity is gaining a deeper understanding of our place in the universe. As we continue to search the stars, the dream of discovering extraterrestrial life is no longer just a fantasy. It is a scientific endeavor, driving us to look ever further into the cosmos. The James Webb Space Telescope, JWST, stands as a monumental leap in humanity's quest to understand the universe, designed with a singular purpose: to look back in time. Through its lens, scientists are able to peer into the earliest epochs of the cosmos, observing the formation of the first galaxies that emerged after the Big Bang. By analyzing these ancient, distant galaxies, researchers hope to unravel how the universe transformed from a hot, dense state into the vast, complex cosmos that surrounds us today. This endeavor is not just about gathering data. It is about rewriting the story of the universe, revolutionizing our understanding of cosmic history and the fundamental forces that shape the cosmos. The JWST's scientific objectives extend far beyond the traditional realm of astronomy. It holds the potential to drive advancements in technology and engineering. The innovations developed specifically for this mission could ripple out into a multitude of fields, sparking progress in optics, material science, and data analysis. In essence, the advancements made in pursuit of JWST's goals are expected to fuel breakthroughs in other industries, offering new tools and methods that will enrich numerous scientific disciplines. However, the JWST is not merely a scientific instrument. It represents a monumental step in human exploration. With its remarkable capabilities, it stands as a testament to the incredible progress we have made in the pursuit of knowledge. Yet, it is not the only technological marvel driving our exploration of the universe. Robotic missions, too, have revolutionized how we understand distant planets and moons, providing insights that were once unimaginable. These sophisticated machines are engineered to travel vast distances, navigate hostile environments, and conduct a wide array of scientific tasks, all without the physical limitations that human explorers face. Robots can endure the unthinkable. They are designed to operate in extreme environments, from the scorching heat of Venus to the freezing cold of Jupiter's moons. Their ability to withstand such conditions allows them to gather data from places that would be impossible for humans to explore. These robotic explorers serve as our proxies, venturing into the unknown where human presence would be unsustainable or too dangerous. One of the most compelling advantages of robotic missions is their capacity to remain operational in space for extended periods. Unlike humans, these machines do not require life support systems or the accommodations necessary for human safety. They are engineered to survive long journeys, persistently analyzing their surroundings and sending back valuable data over years. This capability has proven indispensable in exploring distant planets like Mars. For example, the Mars rovers have vastly expanded our knowledge of the Martian surface. These robotic explorers have analyzed soil and rock samples, captured detailed images, and even found compelling evidence of past water flow on the red planet, which has reshaped our understanding of Mars's potential to host life. More recently, the Curiosity rover, which landed on Mars in 2012, has provided groundbreaking insights into the planet's atmosphere and terrain. This car-sized robot has discovered organic molecules and seasonal methane fluctuations, offering tantalizing clues that Mars may have once supported life. Furthermore, Curiosity's exploration of the Gale crater with its layers of sedimentary rock has allowed scientists to probe the planet's watery past, deepening our understanding of its evolving climate and geology. The most recent rover, Perseverance, which landed on Mars in February 2021, is taking exploration to even greater heights. Equipped with an array of advanced scientific instruments, Perseverance is investigating the Jezero crater, believed to be an ancient lakebed. Its primary mission is to search for signs of past microbial life, not only by examining rock and soil samples, but also by collecting and storing samples for future analysis. Additionally, Perseverance is experimenting with producing oxygen from Mars's thin atmosphere, a crucial step for future human missions to the planet. Looking toward the future, numerous missions are being developed that will continue to push the boundaries of exploration. NASA's Artemis program, for example, aims to return humans to the moon and set the stage for crewed missions to Mars. In a further demonstration of international cooperation, NASA and the European Space Agency are collaborating on the Mars Sample Return mission, which will bring the samples collected by Perseverance back to Earth. This synergy between robotic and human exploration promises to yield deeper insights into Mars and could unlock answers to some of humanity's most profound questions, such as the existence of life beyond our planet. The story of Mars is far from over. With each rover mission, we inch closer to uncovering the secrets of the Red Planet, each new discovery adding a layer of complexity to our understanding of its past, present, and future. These robotic explorers continue to serve as humanity's eyes and ears in the far reaches of our solar system, expanding our knowledge and fueling our curiosity about the cosmos. At the heart of modern space exploration lies international collaboration, a cornerstone that enables countries to join forces and pursue projects that no single nation could undertake alone. By pooling resources, expertise, and technologies, countries can embark on ambitious missions that stretch the limits of human knowledge and capability. A prime example of this is the International Space Station, ISS, a joint venture involving multiple nations. The ISS serves as a platform for research, technological innovation, and international diplomacy, symbolizing the power of collaboration in advancing science and engineering. Working together also fosters the exchange of ideas, methods, and best practices. Different countries bring diverse perspectives to the table, which can lead to creative solutions and innovations that would not emerge in isolation. For instance, the combined strengths of various nations have led to advancements in spacecraft design, enhancing the performance and efficiency of exploratory missions. Furthermore, collaboration allows nations to share the financial burden of large-scale missions, making these endeavors more economically viable and accelerating the pace of progress. International cooperation in space exploration also carries significant geopolitical benefits. By working together on common goals, such as exploring Mars or monitoring climate change from space, countries can foster goodwill and understanding, transcending national borders. In this sense, space exploration serves as a vehicle for peace and stability on Earth, demonstrating the power of collaboration over competition. Beyond the exploration of distant worlds, space missions have also led to significant advancements in our ability to monitor and protect our own planet. Satellite technology, for example, has greatly enhanced our ability to observe Earth's environment, offering crucial insights into climate change, natural disasters, and environmental degradation. As humanity faces increasingly urgent global challenges, these space-based initiatives provide valuable tools for tackling the issues that threaten our planet's future. In conclusion, the continued exploration of space, whether through the eyes of robotic missions like the JWST or the human-driven endeavors of Artemis, holds boundless potential to expand our understanding of the universe. From the first galaxies that formed after the Big Bang to the latest discoveries on Mars, every new piece of information brings us one step closer to answering the most profound questions about our place in the cosmos. As we look to the stars, we do so not as isolated nations, but as a unified species, working together to unlock the secrets of the universe for the benefit of all. International collaboration in the realm of space exploration is not just a catalyst for advancing technological innovation, but also a vital force in shaping the future of science and engineering. As programs designed to connect students and young professionals across borders grow, they facilitate a global exchange of ideas and foster a collective curiosity that transcends national boundaries. These collaborative efforts encourage the development of a new generation of scientists and engineers who share not only a passion for discovery, but also a common purpose. This unity, born from diverse cultural perspectives and backgrounds, enriches the field of space exploration with fresh insights and innovative solutions. As international partnerships expand, the potential for groundbreaking discoveries becomes more promising. We stand at the precipice of a new era in space travel, one where technological advancements, such as reusable rockets and advanced propulsion systems, are poised to revolutionize our approach to the cosmos. These innovations are not merely transforming how we explore space, they are fundamentally altering how we view our place in the universe. One of the most remarkable achievements is the development of reusable launch vehicles. Companies like SpaceX have demonstrated that it is possible to land rocket boosters back on Earth after their mission, a feat that drastically reduces the costs of space travel. This breakthrough not only makes space exploration more sustainable, but it also paves the way for more frequent and affordable missions to distant celestial bodies. Alongside this, electric propulsion technologies like ion drives are emerging as promising alternatives to traditional chemical rockets. Unlike conventional propulsion, which burns fuel to create thrust, ion drives use electricity to accelerate ions, providing a continuous low-thrust output over long periods. This method of propulsion is ideal for deep space missions, enabling us to reach destinations that were once beyond our reach. With such advancements, the vast expanse of the universe seems less distant and more attainable, bringing closer the possibility of exploring the far reaches of the cosmos, Mars, and beyond. As we enhance our propulsion capabilities, the idea of human exploration and colonization of other planets inches ever closer to reality. Technologies such as 3D printing and closed-loop life support systems hold the promise of creating self-sustaining habitats on distant worlds. Imagine constructing structures on Mars from local materials, recycling every bit of waste, and generating life-sustaining resources from within the habitat itself. These innovations would not only enable long-duration missions, but could also support the first permanent human settlements on planets outside of Earth. Furthermore, the integration of artificial intelligence, AI, and robotics into space exploration has opened new frontiers. Autonomous spacecraft and rovers are now capable of performing tasks in hazardous environments, gathering valuable data from planets, moons, and asteroids, all without putting human lives at risk. The synergy between human ingenuity and machine efficiency is allowing us to extend our reach into the cosmos, unraveling mysteries that were once beyond our comprehension. We are now standing on the edge of a golden age of space exploration, one that promises to redefine humanity's role in the vast expanse of the universe. The advancements in technology, coupled with international collaboration, are not just pushing the boundaries of space exploration, they are reshaping our very understanding of the universe and our place within it. Among the most awe-inspiring phenomena in space are gamma-ray bursts. These extremely powerful explosions observed in distant galaxies are the brightest flashes of gamma rays ever detected. They are so intense that they can outshine entire galaxies for a brief moment, often lasting from a few milliseconds to a few minutes. These bursts occur during cataclysmic events, such as the collapse of massive stars into black holes or the collision of neutron stars. The energy released during these events is immense, creating a cosmic spectacle that has fascinated astronomers for decades. The study of gamma-ray bursts offers invaluable insights into the most extreme conditions of the universe. By analyzing the light and energy released during these bursts, scientists can better understand the life cycles of stars and the processes that lead to the formation of black holes. These bursts also serve as cosmic markers, allowing researchers to study ancient galaxies and the conditions that existed when the universe was in its infancy. The light from these bursts can travel billions of years, providing a unique glimpse into the early universe and shedding light on the formation of stars and galaxies. As such, gamma-ray bursts are not only crucial to our understanding of astrophysics, but are also key to unlocking the mysteries of cosmology. Similarly, quasars and pulsars continue to push the boundaries of our knowledge. Quasars, or quasi-stellar objects, were first discovered in the 1960s as intensely bright sources of energy. These objects are powered by supermassive black holes at the centers of distant galaxies, surrounded by an accretion disk of gas and dust. As this material accelerates and heats up to extreme temperatures, it emits vast amounts of radiation, making quasars some of the most luminous objects in the universe. They offer astronomers a powerful tool for probing the nature of black holes and the evolution of galaxies across cosmic time. Pulsars, on the other hand, are rapidly rotating neutron stars that emit beams of electromagnetic radiation. When these beams are directed towards Earth, they appear to pulse with remarkable regularity, much like a cosmic lighthouse. The discovery of pulsars in the 1960s challenged existing theories of stellar evolution and the behavior of matter in extreme conditions. These small, dense remnants of massive stars, typically only a few kilometers in diameter, are so compact that their mass exceeds that of the Sun, yet they occupy a fraction of the volume. By studying pulsars, scientists gain critical insights into the fundamental forces of nature, including gravity, electromagnetism, and nuclear forces. Both quasars and pulsars continue to challenge our understanding of the universe. The study of these phenomena helps astronomers explore the mysteries of black holes, galaxy formation, and dark energy. Pulsars, with their extreme environments, provide a natural laboratory for studying the behavior of matter and forces in conditions that cannot be replicated on Earth. Together, these cosmic objects are reshaping our understanding of astrophysics and deepening our appreciation for the intricate and interconnected fabric of the universe. Another enigmatic phenomenon that has captured the attention of astronomers is fast radio bursts, FRBs. These brief yet incredibly powerful bursts of radio waves were first detected in 2007, originating from galaxies far beyond our Milky Way. Despite their short duration, FRBs can release more energy in a single instant than the Sun does in an entire day. Their extreme brightness makes them detectable across vast cosmic distances, and their mysterious nature has made them the subject of intense study. The origins of these bursts remain unclear, with theories ranging from rapidly rotating neutron stars, similar to pulsars, to more exotic possibilities, such as black hole mergers or even signals from extraterrestrial civilizations. Each of these hypotheses presents fascinating questions about the nature of the universe. Could these bursts be the result of cataclysmic cosmic events? Or is it possible that they represent the first hints of communication from intelligent life beyond our solar system? As scientists continue to investigate these bursts, they are not only pushing the boundaries of astrophysical research, but also exploring the possibility of discovering new forms of life or intelligence in the universe. In every corner of the cosmos, there are phenomena that challenge our current understanding of space and time. From gamma-ray bursts to fast radio bursts, quasars to pulsars, each discovery brings us one step closer to unraveling the mysteries of the universe. And with each new revelation, humanity is invited to look deeper into the fabric of space, to ask more questions and to seek answers that will expand our knowledge and understanding of the vast cosmos that surrounds us. Fast radio bursts, FRBs, have emerged as one of the most intriguing and enigmatic phenomena in modern astronomy. These intense, high-energy bursts of radio waves, lasting mere milliseconds, travel across vast distances, often originating from distant galaxies far beyond our own. As these signals journey through the cosmos, they interact with the matter and radiation in their path. This interaction offers a unique opportunity for astronomers to study the intergalactic medium, the elusive space between galaxies, and the distribution of matter throughout the universe. FRBs, though seemingly brief, carry profound information that can enhance our understanding of the universe's intricate structure. By analyzing these bursts, scientists can refine their theories about cosmic evolution and the large-scale formation of the universe. But fast radio bursts are not just signals. They are cosmic clues that help us solve some of the universe's deepest mysteries. Each burst invites researchers to probe questions that have baffled us for centuries, from the birth and life cycles of stars to the possibility of intelligent life elsewhere in the cosmos. What makes FRBs particularly fascinating is their potential to challenge our understanding of fundamental cosmic processes. As astronomers continue to study these signals using state-of-the-art technology and international collaboration, we find ourselves on the edge of a discovery that could reveal new truths about the structure of the universe, perhaps even those we haven't yet imagined. Meanwhile, gravitational waves, ripples in the fabric of space-time, have opened an entirely new way to observe the cosmos. First predicted by Albert Einstein over a century ago, these waves are the result of the most extreme and dynamic events in the universe. Gravitational waves were a theoretical concept for decades, but in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made a groundbreaking detection, marking a historic moment in the field of astrophysics. These ripples, produced by the collision of massive celestial bodies like black holes or neutron stars, travel across space at the speed of light. As they pass through Earth, they distort the very fabric of space-time. The unique properties of these waves, such as their frequency and amplitude, provide valuable insights into the characteristics of their sources, such as the mass of the objects involved and their relative motion before the collision. This allows scientists to learn about cosmic events that occurred billions of light years away, from the merger of black holes to the explosive deaths of stars. Gravitational waves have transformed the way we observe the universe. Unlike light-based observations, gravitational waves can penetrate areas of the cosmos where light is absent, such as in the case of black hole mergers, which occur without emitting any visible radiation. This gives us access to cosmic phenomena that are otherwise hidden, providing a richer and more comprehensive view of the universe's workings. As the technology to detect gravitational waves improves, scientists anticipate even more groundbreaking discoveries, shedding light on the formation and evolution of galaxies, the nature of dark matter, and the fundamental laws that govern the cosmos. In a similar vein, the transit method of exoplanet detection has completely revolutionized our understanding of distant worlds. By monitoring the light emitted from a star and detecting the slight dimming caused by a planet passing in front of it, astronomers can infer essential information about the planet, such as its size, orbital period, and distance from its host star. This method has dramatically expanded our catalog of exoplanets, revealing thousands of new worlds that exist beyond our solar system. Prior to the advent of this method, the discovery of exoplanets was a challenging task, relying on indirect measurements that often only identified large gas giants similar to Jupiter. However, the transit method allows scientists to detect smaller, Earth-sized planets in the so-called habitable zone, where conditions might support liquid water and possibly life. This breakthrough has not only deepened our understanding of exoplanets, but also brought us closer to answering one of humanity's most profound questions. Are we alone in the universe? As astronomers gather more data from these transits, they can also analyze the atmospheric composition of distant exoplanets. By observing the light that filters through a planet's atmosphere during a transit, scientists can detect various gases, such as water vapor, carbon dioxide, and methane, that could indicate biological processes. This capability has opened up new possibilities for studying the habitability of distant planets, suggesting that the universe may be teeming with life in ways we have yet to fully comprehend. However, not all cosmic mysteries are so easily solved. Throughout the history of science, there have been anomalies that challenge our understanding of the universe and defy explanation. Dark matter is perhaps one of the most perplexing. Despite comprising about 26% of the universe, it remains invisible and undetectable by conventional means. We know it exists due to its gravitational effects on galaxies and other cosmic structures, yet its exact nature remains a complete mystery. Even more enigmatic is dark energy, an unseen force responsible for the accelerated expansion of the universe. Dark energy makes up around 70% of the cosmos, yet we have only the faintest understanding of how it works. Scientists are still grappling with the implications of dark energy on the fate of the universe. And then there is quantum mechanics, which presents its own set of perplexing phenomena, such as quantum entanglement. This bizarre behavior, where particles become instantaneously connected across vast distances, challenges everything we thought we knew about space and time. Perhaps the most extraordinary of all the cosmic enigmas are the fast radio bursts, which have taken the astronomy world by surprise. These high-energy bursts of radio waves, coming from unknown corners of the universe, have sparked heated debates among scientists. Theories about their origins range from exotic astrophysical phenomena to even the possibility of advanced extraterrestrial technologies. No matter the source, these anomalies underscore the progress we have made in understanding the universe and the limits of our knowledge. As we continue to unravel the mysteries of the cosmos, the concept of space colonization has gone from a far-fetched idea to a serious pursuit. With growing interest in exploring other celestial bodies, particularly Mars and the Moon, discussions about the feasibility of human settlements in space are gaining momentum. To make this extraordinary vision a reality, we must overcome significant challenges in technology, engineering, and life support systems. One of the most pressing hurdles is the development of reliable transportation systems capable of carrying humans on long journeys. To reach Mars or the Moon, spacecraft must be designed to support life for extended periods, providing astronauts with the necessary resources and safety throughout the mission. As technology advances, the dream of human colonization beyond Earth may one day come to fruition, opening up new frontiers for exploration, survival, and discovery. With each new breakthrough, we inch closer to unraveling the mysteries of the cosmos and our place within it. The universe is vast, and its secrets are many. But as we venture further into the unknown, we continue to seek answers that have the potential to transform our understanding of reality itself. The cost of space exploration has long been one of its most formidable barriers. While technological advancements in reusable rocket systems have significantly lowered the cost of launching payloads into space, securing adequate funding remains a crucial factor. This funding is dependent not only on the financial commitments of governmental space agencies, but also on the growing participation of private enterprises. These collaborations between public and private sectors will be essential in making space exploration sustainable in the long term. Upon reaching our destination, the challenges only intensify. One of the most pressing issues is creating habitats capable of supporting human life in environments that are incredibly hostile to our biology. Take Mars, for example. Its atmosphere is primarily composed of carbon dioxide, and its surface temperatures can drop to levels far colder than anything experienced on Earth. Colonizing such a planet would require developing entirely new methods for sustaining human life. In the absence of Earth's familiar resources, colonies will need self-sustaining systems that can produce food, water, and oxygen. To address this, researchers are exploring groundbreaking methods like growing crops in controlled artificial environments. They are also investigating the possibility of utilizing resources found directly on the planet, an approach known as in situ resource utilization. This technique would enable settlers to rely less on supplies sent from Earth, easing the logistical burden of space missions. It is a monumental shift from the conventional paradigm of relying entirely on Earth-based resources. However, the technological and logistical hurdles are only part of the challenge. Sociopolitical and psychological aspects must also be considered. Establishing a permanent human presence in space means addressing questions of governance, laws, and social structures in a setting completely unfamiliar to any Earth-bound civilization. There will be no immediate blueprint for how to handle disputes, rights, or communal living in space. More than this, we must ensure that human beings can adapt to living in isolation far from home. The psychological impact of long-term space missions, where individuals may find themselves cut off from Earth for extended periods, is a critical factor that cannot be ignored. The emotional and social dynamics of space communities will require careful planning, as living in close quarters for months or even years could strain relationships. Overcoming these multifaceted challenges is not optional. It is essential for ensuring that space colonization shifts from being a distant dream into a tangible reality. One of the most exciting developments in space exploration in recent years is the potential for asteroid mining. Once the stuff of science fiction, the concept of extracting valuable resources from asteroids and other celestial bodies has moved into the realm of serious scientific and economic conversation. Estimates suggest that there are resources worth up to $10 quintillion floating within our solar system, providing an unprecedented opportunity for expansion. Asteroids, in particular, are believed to contain precious metals like platinum, gold, and rare earth elements. materials that could not only fuel further space exploration, but also have wide-ranging applications on Earth. Organizations and private companies are already formulating plans to mine these resources. NASA, for instance, has been at the forefront of this effort, spearheading missions such as the OSIRIS-REx mission, which successfully collected samples from the asteroid Bennu. These samples will provide valuable insights into the composition and history of asteroids, ultimately guiding future mining operations. At the same time, companies like Planetary Resources and Deep Space Industries are working to develop the technologies necessary to locate, mine, and transport resources from asteroids. Their goal is not only to supply resources for Earthbound industries, but also to create a sustainable economy in space. These companies envision an entire new sector, one in which space-based resources can support human endeavors both on Earth and in space. The benefits of asteroid mining extend far beyond just the extraction of rare metals. By utilizing space-based resources, we can reduce our dependence on terrestrial mining, thereby mitigating the environmental impacts associated with mining on Earth. The environmental cost of resource extraction on our planet is immense, from habitat destruction to pollution, and asteroid mining could help lessen these impacts. Moreover, space mining promises to open new avenues for space exploration, creating a virtuous cycle that supports both commercial ventures and further scientific research. One of the most alluring aspects of space exploration in the modern era is the rapidly developing industry of space tourism. Once considered the domain of speculative fiction, space tourism is now on the cusp of becoming a reality. Companies like SpaceX, Blue Origin, and Virgin Galactic are already conducting suborbital flights, allowing ordinary citizens to experience the awe-inspiring weightlessness of space and the breathtaking view of Earth from nearly 200 miles above the surface. As technology continues to improve and the cost of space travel decreases, the dream of traveling into space will likely become more accessible to a broader segment of the population. Space tourism is poised to become a multi-billion-dollar industry. Future developments may include not just suborbital flights, but longer stays in low Earth orbit and even trips to the moon and beyond. Imagine hotel chains in space, offering breathtaking views of our planet, where guests can enjoy the ultimate vacation experience. The economic potential of space tourism is staggering, creating new job opportunities not only in the aerospace sector, but also in hospitality, transportation, and a host of other industries. But the implications of space tourism go beyond just economic growth. More people experiencing space could lead to a profound shift in our understanding of our planet's fragility. Viewing Earth from the vantage point of space often ignites a deep sense of awe and responsibility. Travelers may return home with a newfound commitment to environmental preservation, motivated to advocate for sustainable practices and climate change action. The experience of seeing Earth as a tiny, vulnerable dot in the vastness of the cosmos could inspire a collective sense of stewardship for our planet. Space tourism could also have a profound impact on the next generation. As more people become familiar with space travel, we may see an increase in interest in science, technology, engineering, and mathematics, STEM fields. Young minds inspired by the idea of venturing beyond Earth could pursue careers in aerospace, engineering, and planetary science, helping to drive forward human progress in space. In this way, space tourism is not just a leisure activity, it's a gateway to igniting a new wave of scientific exploration and technological innovation. As humanity pushes further into the cosmos, ethical questions surrounding our exploration of space become increasingly complex. How should we interact with other celestial bodies? Should we attempt to make contact with potential extraterrestrial civilizations? These questions raise profound moral dilemmas. Foremost among these concerns is the preservation of the environments we explore. As we venture to planets like Mars or moons like Europa, many argue that we bear the responsibility of protecting these places from contamination. The risk of introducing Earth's microbes into alien ecosystems could have unforeseen consequences, which is why many space agencies are working to develop strict protocols to prevent such contamination. Equally contentious is the question of extraterrestrial intelligence. Should we broadcast our existence to other civilizations, or would such actions be too dangerous? Some scientists advocate for a cautious approach, arguing that announcing our presence could invite risks, while others believe that the potential benefits of contact, such as new knowledge or technological advancements, could outweigh the dangers. The debate over how to approach potential extraterrestrial life is ongoing, and it is one that will shape the future of humanity's relationship with the cosmos. Complicating these discussions are issues of ownership and resource exploitation. As countries and private companies gear up to harvest resources from asteroids or other celestial bodies, questions arise about who has the right to claim these resources. Should they be treated as the common heritage of all humanity, or should individual entities have the right to extract and profit from them? This issue mirrors the ethical dilemmas we face on Earth, such as the challenges of wealth inequality and environmental degradation. The rules we establish for space exploration and resource sharing could have far-reaching consequences, not only in the cosmos, but also here on Earth. By fostering cooperation rather than competition, we can create a model for space exploration that avoids the pitfalls of territorial disputes and environmental exploitation. The future of space exploration is not just about technology. It's also about the values we choose to carry with us into the universe. Space exploration stands as one of the most profound frontiers in humanity's quest to understand its place in the vast cosmos. As we chart our course into the stars, the choices we make today concerning how we approach distant worlds and potential sentient beings will shape not just our interactions with space, but also our ethical frameworks here on Earth. These decisions are not merely practical, they carry deep moral and philosophical weight. Engaging in this discourse prepares us for the extraordinary possibilities ahead, while prompting us to reflect on our values as a species. The sky may appear as the ultimate frontier, but the ethical ground we stand upon must be carefully examined and fortified before we venture further. At the heart of this journey lies a revolution in propulsion technologies that promises to transform how we explore the cosmos. Traditional chemical rockets, which have served humanity since the dawn of space exploration, are constrained by their inefficient use of fuel and the immense energy required to break free of Earth's gravitational pull. Emerging propulsion systems, however, offer revolutionary pathways to expand our reach, cut down travel times, and open new frontiers in space exploration. One such breakthrough is ion propulsion, which uses electric fields to accelerate ions, generating thrust with exceptional efficiency. Unlike conventional rockets, ion propulsion consumes far less fuel, enabling spacecraft to journey much farther, faster. Missions that once took months or even years could now take weeks, opening the door to ambitious missions to Mars, asteroids, and beyond. This efficiency also makes it possible to conduct more frequent missions, thereby multiplying the potential for scientific discovery. Another exciting development is nuclear thermal propulsion, which utilizes the power of nuclear reactors to heat a propellant, significantly boosting thrust. This method holds the promise of faster travel to distant destinations like Mars, cutting down on the time astronauts spend exposed to the harsh conditions of space. By reducing the exposure to radiation and microgravity, nuclear thermal propulsion not only promises a safer journey, but also enhances the chances of long-term human survival on another planet. Beyond these practical technologies, researchers are exploring even more exotic concepts like solar sails, which use the momentum of photons from the sun to propel spacecraft. These sails could allow for prolonged missions with minimal fuel, offering a sustainable way to explore the outer reaches of our solar system. And though warp drives remain the stuff of science fiction, their theoretical potential for faster-than-light travel continues to capture the imaginations of scientists and dreamers alike. These advancements do not represent mere incremental steps forward, but rather a transformative leap in our capacity to explore the universe. As humanity gazes ever more intently toward the stars, the prospect of manned missions to Mars remains one of our most ambitious goals. With current projections suggesting that astronauts could set foot on the red planet within the next 2 decades, both NASA and private companies like SpaceX are actively developing the advanced technologies necessary to make this journey a reality. These missions will face numerous challenges. designing life support systems, protecting astronauts from radiation, and ensuring sustainable practices for long-term stays on the Martian surface. But these challenges are not merely obstacles, they are opportunities to push the boundaries of what humanity can achieve. The goal is not only to visit Mars, but to establish a permanent human presence on the planet. Plans are already in motion to send robotic probes ahead of human crews, laying the groundwork for future settlements by exploring the Martian environment, establishing habitats, and conducting experiments to determine how to utilize local resources. Once we master the challenges of Mars, the Moon will serve as a vital stepping stone for even more ambitious missions. NASA's Artemis program, aimed at landing astronauts on the lunar surface, is preparing the way for sustainable lunar exploration. This not only helps refine the technologies needed for longer duration space missions, but also provides a base for planetary science and the staging of future interplanetary expeditions. Looking farther into the future, the moons of Jupiter and Saturn, Enceladus, Europa, and Titan present tantalizing possibilities for exploration. While these missions may be decades or even centuries away, renewed interest in exploring such distant worlds suggests that they may one day become a reality. The drive to reach these destinations remains strong, fueled by a sense of wonder and the relentless human quest for discovery. As we journey deeper into the cosmos, our cultural interpretations of space evolve with us. Throughout history, humans have viewed the universe through myriad lenses, each shaped by the values, beliefs, and technological advancements of their time. In ancient civilizations, the stars were often seen as gods or omens, with celestial bodies playing a central role in agriculture, governance, and cultural mythology. In Mesopotamia, for example, the movements of the stars were intricately linked to earthly affairs, shaping everything from the calendar to the decisions of kings. The constellations were more than mere patterns. They were stories, integral to the culture's identity. Over time, scientific inquiry began to shift these mythological views, gradually introducing more systematic and empirical models of the universe. Ancient Greek philosophers like Ptolemy and Aristotle placed Earth at the center of the universe, a geocentric view that dominated for centuries and aligned with the belief that humanity was the focal point of existence. But this worldview was dramatically challenged during the Renaissance by figures like Copernicus, Galileo, and Kepler, who proposed a heliocentric model where the sun, rather than the Earth, was at the center of the solar system. This shift marked a profound change in how humanity understood its place in the universe and paved the way for modern scientific exploration. The invention of the telescope further expanded our understanding, allowing us to peer deeper into the cosmos and discover new realms, planets, moons, and galaxies previously hidden from view. The 20th century ushered in the space age, where the launch of satellites and human space travel ignited the collective imagination, sparking philosophical debates about our place in the universe and the possibility of life beyond Earth. Today's continues to captivate our curiosity, blending scientific knowledge with cultural narratives, from movies and literature to art and religion. Our interpretations of space are more nuanced than ever before, exploring not only the physical properties of the cosmos, but also the existential questions it raises about the nature of life, consciousness, and the future of humanity. Science fiction, too, has played a crucial role in shaping our understanding of space. Serving as a fertile ground for imagination, science fiction allows both scientists and the public to explore the possibilities that lie beyond our planet. Iconic authors like Arthur C. Clarke and Isaac Asimov have not only entertained millions, but have also inspired generations of scientists to consider what might be possible in the realm of space exploration. The speculative narratives of science fiction offer a unique blend of entertainment and intellectual stimulation, often tackling complex scientific principles, such as the laws of physics, time dilation, and faster-than-light travel, in ways that make them accessible and engaging. Though many of these concepts remain theoretical, they continue to stimulate important conversations and research that push the boundaries of what we think is possible. In this sense, science fiction acts as a bridge between established scientific knowledge and future innovations. It inspires both imagination and innovation, sparking the ideas and technologies that will one day make the exploration of distant worlds a reality. As we venture into the unknown, these speculative stories remind us of the endless possibilities that lie ahead. Through exploration, discovery, and imagination, we come closer to understanding not just the universe, but our own potential as a species. The visual portrayal of space in science fiction has had an undeniable impact on shaping public interest in the cosmos, transcending the boundaries of mere entertainment. Films like Interstellar and the Star Wars franchise have captivated audiences, igniting a sense of awe and wonder that goes beyond the cinematic experience. They transport viewers into the boundless expanse of the universe, helping them grasp its immense scale and contemplate the possibilities of life beyond Earth. In doing so, these iconic films do more than entertain. They spark curiosity and fuel a broader cultural fascination with space exploration. This collective imagination, in turn, nurtures greater public support for scientific endeavors, leading to increased investments and funding for projects aimed at exploring the unknown. The fusion of science fiction with real-world innovation has become more pronounced in recent years. SpaceX, for example, has set its sights on Mars colonization, a mission that once seemed like the stuff of speculative fiction. Today, it is increasingly within reach. These once fantastical ideas are evolving into tangible, science-backed projects, shaping the modern narrative of space exploration. As we edge closer to making what was once fiction a reality, our understanding of space and humanity's place within it is continually. They didn't just build for the sake of construction. Their works were physical manifestations of spiritual beliefs and scientific understanding. They combined art, astronomy, and religion, forming a holistic view of the cosmos that integrated the celestial with the terrestrial. Each of these ancient sites is a testament to the innate curiosity that has driven humans to look up and ask the fundamental questions. What is out there, and what is our place in it? The answers to these questions, though still evolving, link us to those who came before, a long chain of inquisitive minds stretching back through the millennia. A strikingly profound psychological phenomenon known as the overview effect occurs when astronauts view Earth from space. From this vantage point, Earth appears as a tiny, fragile oasis suspended in the vastness of space. Surrounded by the infinite dark expanse and the thin, delicate blue atmosphere, astronauts often experience a deep emotional connection to all of humanity. The boundaries that divide us on the surface, countries, states, and regions, seem arbitrary when seen from above. In that moment, Earth is one unified entity, and the realization that we share one planet, one life-sustaining environment, becomes unmistakably clear. Many astronauts report feeling a profound shift in perspective after witnessing the Earth from space. They return with an urgent sense of responsibility, realizing the fragility of our planet and the pressing need to protect it. Their stories, shared through books, interviews, and documentaries, resonate with audiences worldwide, influencing people who may never leave Earth, but are nonetheless moved by the emotional weight of these accounts. The overview effect has the potential to inspire societal change by triggering conversations about environmental stewardship and the need for global action. Astronauts' reflections on their experiences in space serve as a powerful call to action. The images they share, a planet floating in the void, have the ability to spark a new sense of urgency about sustainability. Their emotional testimonies encourage viewers to see our world as a precious, shared resource that requires collective care. As more individuals become attuned to the Earth's fragility, there is the potential for a cultural shift, one in which planetary health becomes a priority for all. The overview effect thus carries the potential to unite people from all corners of the globe, creating a new generation of Earth stewards. Art and storytelling have also played a crucial role in shaping how we view space exploration. Through vivid imagery, compelling narratives, and evocative themes, art has the ability to capture the wonder and excitement of space, sparking public curiosity and driving interest in scientific discovery. Whether through novels, films, or visual art, these forms of expression allow people to envision possibilities beyond their immediate surroundings, offering a sense of adventure that is often linked to the mysteries of the universe. Science fiction, in particular, provides an avenue for imagining life beyond Earth, blending human experiences with extraterrestrial exploration. These narratives often reflect our deepest desires and fears, exploring themes of bravery, survival, and the unknown. They make complex scientific concepts more accessible and emotionally resonant, helping audiences connect with ideas about space that might otherwise feel abstract or distant. Visual art, from traditional paintings to cutting-edge digital creations, also plays a significant role in shaping the public's perception of space. Artists interpret celestial phenomena, turning data into beautiful works of art that are as scientifically accurate as they are visually stunning. These creations evoke awe and wonder, encouraging people to engage more deeply with space science. As a result, public interest in space missions and research initiatives is often sparked or enhanced by these artistic endeavors, showing that the visual and the scientific can work in tandem to inspire a greater collective interest in space exploration. Through both science fiction and visual art, storytelling acts as a bridge, connecting the far reaches of space with the human experience. These artistic expressions do more than tell stories. They shape the way we think about the universe, pushing us to look beyond the confines of Earth and imagine a future where humanity ventures beyond the stars. In this way, art and science work hand in hand, fueling a passion for discovery that spans generations. Moreover, public interest in space exploration and scientific discovery is often amplified through engaging events like exhibitions, science fairs, and educational programs that blend art with science. These events have the power to merge creativity with research, fostering a community that appreciates the artistry involved in exploring the universe. By showcasing the intersection of art and science, these programs not only spark curiosity, but also create a sense of unity. They cultivate an environment where people from all walks of life can engage with the wonders of space and feel connected to the ongoing pursuit of knowledge. Space has always been a realm of mystery and beauty, a place that evokes awe and wonder. The images captured from space offer more than just a glimpse of distant galaxies. They carry with them profound stories of creation, destruction, and evolution. One of the most iconic images is the Hubble Space Telescope's awe-inspiring view of the Pillars of Creation. Located in the Eagle Nebula, these towering columns of gas and dust are the birthplaces of new stars. The vibrant colors that define this image tell a tale not only of beauty, but of the dynamic processes that govern the universe. It is an image that captures the essence of cosmic birth, stirring our imagination as it showcases the very fabric of star formation. Another image that resonates deeply with people is the famous pale blue dot photograph taken by the Voyager 1 spacecraft. From a distance of approximately 3 billion miles, Earth appears as a mere speck of light against the backdrop of the vast cosmos. In this tiny dot, we find our home, a stark reminder of the fragility of our existence. This photograph inspired the words of Carl Sagan, who reflected on the unity of humanity on this small speck, urging us to reconsider our place in the universe. The image raises deep philosophical questions about our role in the grand expanse of space and serves as a reminder that despite the vastness of the cosmos, we are all part of the same fragile world. The cosmic microwave background radiation image captured by the Planck satellite provides yet another compelling view of the universe's origins. It represents the faint heat left over from the Big Bang, the moment when the universe began to expand. The irregular patterns and temperature fluctuations seen in this image are not just scientific, they are clues to the fundamental nature of the cosmos. For many, this image serves as a direct link to the beginning of everything, sparking curiosity about how the universe has evolved over the billions of years since its inception. In addition to these, the Hubble Space Telescope has provided some of the most remarkable images of distant galaxies. The ultra-deep field, for example, reveals thousands of galaxies, each containing billions of stars scattered across the vast reaches of space. These images offer us a chance to peer into the past, as the light we see today has traveled for billions of years, carrying with it the history of the universe. The enormity of these images brings into sharp focus the unimaginable scale of the cosmos, raising questions about the countless possibilities that exist beyond our own galaxy. Eclipses, both solar and lunar, are captivating celestial events that occur when one astronomical body moves into the shadow of another. A solar eclipse takes place when the moon passes between the Earth and the Sun, casting its shadow and briefly blocking the Sun's light. On the other hand, a lunar eclipse occurs when the Earth moves between the Sun and the Moon, casting its shadow over the Moon. Although predictable, these events continue to inspire wonder and awe, reminding us of the intricate dance of celestial bodies that shapes our sky. Throughout history, eclipses have captivated human imagination. Many ancient cultures saw eclipses as powerful omens. In ancient China, a solar eclipse was believed to signal the emperor losing favor with the heavens, often prompting elaborate rituals to appease cosmic forces. Similarly, the Greeks viewed eclipses with a mix of fear and reverence, with philosophers like Aristotle linking them to significant events in nature and politics. For the Maya, eclipses marked both times of change and cosmic reckoning, intertwined with their complex understanding of the universe. Lunar eclipses were especially sacred in many indigenous cultures, woven into community rituals and storytelling traditions. While modern science has unraveled the mechanics behind these phenomena, eclipses still hold cultural significance. Total solar eclipses, which can only be seen from specific geographical locations, bring people together in excitement and awe. These rare moments offer a unique opportunity for collective reflection and wonder. As we, despite these technological challenges, CMEs also enhance the beauty of our skies by creating more vibrant auroral displays. The interplay between solar activity and Earth's atmosphere underscores the dynamic relationship between our planet and the Sun. Magnetars, a type of neutron star, are some of the most extraordinary and mysterious objects in the universe. They are the remnants of massive stars that have undergone supernova explosions, and their magnetic fields are among the strongest known in the cosmos. These magnetic fields can be 1,000 million times stronger than Earth's, affecting the surrounding space in profound ways. A magnetar's magnetic field is so intense that it can cause the star's crust to shift suddenly, triggering starquakes that release more energy in a fraction of a second than the Sun does in thousands of years. This immense energy release is part of what makes magnetars such fascinating objects for astronomers and physicists alike. They offer a glimpse into the most extreme conditions in the universe, where the laws of physics behave in ways that challenge our understanding. As scientists continue to study magnetars, they uncover new insights into the fundamental forces that shape our universe, making them some of the most powerful and intriguing objects in the cosmos. Moreover, the magnetic field surrounding a magnetar is so incredibly intense that it has the power to distort the very fabric of space-time itself. This profound influence can lead to strange and unexpected effects, such as altering the trajectories of particles that venture too close and even bending the flow of light itself. The combination of extreme radiation and magnetic forces creates an environment that is not just scientifically captivating, but also one of great danger for any matter that dares to approach. Over the years, scientists have intensively studied these enigmatic cosmic objects, hoping to unlock the secrets This delicate balance of energy allows for moderate temperatures that have made Earth uniquely suited for life. Another crucial cosmic factor to consider is the phenomenon of supernovae, violent explosions marking the death of massive stars. These cataclysmic events not only reshape the cosmos, but they can also disrupt the formation of new stars and even alter the composition of planetary atmospheres. When a supernova occurs, it releases an immense amount of energy and sends shockwaves through space. The remnants of these stellar explosions spread heavy elements like carbon and oxygen, elements essential for life as we know it. Thankfully, the nearest supernova remnants are far enough away from Earth that they pose no immediate threat. However, if one were to occur too close, it could expose the Earth to harmful radiation, potentially endangering life on the planet. Jupiter's gravitational influence has been another key factor in safeguarding Earth's habitability. As the largest planet in our solar system, Jupiter's immense size creates a protective barrier against the frequent barrage of comets and asteroids that could otherwise threaten the inner planets, including Earth. By stabilizing the orbits of objects in the asteroid belt and the distant Kuiper belt, Jupiter helps to reduce the likelihood of catastrophic collisions with Earth. While cosmic events undoubtedly pose risks to our planet, they have also played a crucial role in establishing the conditions that make Earth capable of sustaining life. Meteorite impacts have been significant catalysts in shaping both the geological and biological history of Earth. These cosmic collisions have the power to dramatically alter landscapes, creating massive craters and ejecting materials into the atmosphere, which can influence global climates. One of the most well-known impacts is the Chicxulub impact, which occurred roughly 66 million years ago in what is now Mexico. This event is widely believed to have contributed to the mass extinction that wiped out approximately 75% of Earth's species, including the dinosaurs. The aftermath of this impact resulted in drastic climate changes, including temperature drops and disruptions to ecosystems. However, this event also opened up ecological niches that allowed mammals to thrive and diversify, eventually leading to the rise of species like humans. Geologically, these impacts all contribute to the formation of unique rock types and structures. When a meteoroid strikes Earth, the intense heat and pressure can melt and vaporize rock, leading to the formation of impactites, rocks created specifically by meteorite impacts. These materials can be rich in various minerals and other elements that influence local geology. In some cases, these elements may even provide valuable resources for future life forms to exploit. Biologically, the effects of meteoric impacts can be both immediate and long-lasting. The debris thrown into the atmosphere can block sunlight, causing dramatic temperature drops and disrupting the delicate balance of photosynthesis. In the long run, these catastrophic events can spur evolutionary changes. For example, after the extinction of the dinosaurs, mammals rapidly evolved and diversified, leading to the development of a wide variety of species, including humans. This highlights a profound connection between cosmic events and biological evolution. Meteorite impacts are not merely destructive forces, they are also integral to the evolutionary process, reshaping not just Earth's physical landscape, but the very trajectory of life on the planet. The solar system itself remains a vast, uncharted frontier, brimming with mysteries that beckon to be explored. Beyond the orbit of Neptune lies the Kuiper belt, a region teeming with icy bodies, including the dwarf planet Pluto. While the New Horizons mission provided us with invaluable data, much of the Kuiper belt remains unexplored. Scientists believe that the objects in this distant region could hold critical clues about the early formation of the solar system and the building blocks of planets. Further out, we find the intriguing realm of the Oort cloud, a hypothetical spherical shell surrounding the solar system. This region is thought to be the source of long-period comets, though no spacecraft have ventured out to explore it. Located at distances of over 100,000 astronomical units from the Sun, the Oort cloud remains a distant, unexplored region of the solar system. The exploration of this outermost frontier could offer groundbreaking insights into the solar system's formation and even reveal how other star systems might evolve. In addition to the icy reaches of the Kuiper belt and the Oort cloud, there are other compelling destinations within our solar system that warrant closer examination. For example, Europa, one of Jupiter's many moons, has a thick ice shell that may conceal a vast ocean beneath. This hidden environment presents an enormous opportunity for astrobiologists, as the potential for life or prebiotic conditions in Europa's subsurface ocean is a tantalizing possibility. Missions aimed at drilling through Europa's icy crust could yield crucial data about the moon's potential for supporting life, as well as broader insights into the conditions required for life to emerge beyond Earth. In exploring these uncharted territories, we seek not only to understand the formation of our own solar system, but to answer larger questions about the nature of life and the potential for life elsewhere in the universe. Each mission, each discovery, brings us closer to understanding the grand tapestry of the cosmos and our place within it. The future of space exploration holds the promise of answers to some of the most profound mysteries that have fascinated humanity for centuries. Asteroids in the belt between Mars and Jupiter represent a fascinating and often overlooked part of our solar system. While groundbreaking missions like Japan's Hayabusa and NASA's OSIRIS-REx have successfully returned samples from these ancient space rocks, many of these celestial bodies remain unexplored. The potential of studying these asteroids is immense. By investigating them, scientists could unlock crucial clues about the organic molecules and water that were essential for the development of life on Earth. In addition, asteroid mining, still a far-off prospect, could one day provide vital resources for human exploration beyond Earth. Thus, every uncharted corner of our solar system isn't just a geographical puzzle. It's a vast opportunity for discovery and deeper understanding. The prioritization of space missions, especially to distant or unknown bodies, hinges on multiple factors, each more complex than the next. It is not a simple decision. It is shaped by scientific objectives, the promise of new discoveries, and the availability of the necessary resources for exploration. When space agencies like NASA propose missions, they start by identifying the goals they want to achieve. These goals could vary: studying a planet's geology, probing its atmosphere, searching for signs of life, or even unraveling the origins of our entire solar system. The potential for groundbreaking discoveries is one of the primary drivers behind mission selection, yes, but it's far from the only one. A critical factor in evaluating mission targets is feasibility. What technology is available? How long will the journey take? What are the costs associated with the mission? Missions to far-off destinations like Uranus or Neptune face the additional hurdles of extremely long travel times, the challenge of maintaining communication across vast distances, and the difficulty of sustaining energy supplies for extended periods. On the other hand, missions to nearer objects like asteroids or moons within our immediate reach tend to be more attractive. These missions promise a higher chance of success within realistic budgets and timelines. The relative ease of reaching these destinations makes them a priority for agencies looking to deliver tangible results. Scientific collaboration also plays a pivotal role in determining which missions rise to the top. Agencies such as NASA and the European Space Agency, ESA, are not working in isolation. They rely heavily on input from the global scientific community. Research proposals are submitted, peer-reviewed, and evaluated to ensure that the final mission plan reflects a broad range of scientific perspectives and expertise. Furthermore, missions that offer the potential for international cooperation are often more appealing. By pooling financial resources and expertise, these collaborations not only reduce the burden on individual nations, but also enhance the chances of a mission's success. When the world comes together, it often leads to more powerful outcomes. Yet, there's another element that cannot be underestimated: public interest. Missions that ignite the imagination of the public, missions that promise to explore captivating targets like Mars or Europa, a moon of Jupiter that may harbor subsurface oceans, tend to attract more support and funding. The excitement surrounding these missions is contagious, influencing decisions that reverberate at the highest levels of space agencies and government. The public's fascination with these tantalizing possibilities becomes a driving force, helping to guide the future of space exploration. As we consider the prioritization of space missions, we see how a balance must be struck between scientific merit, practical limitations, international collaboration, and public enthusiasm. This intricate framework not only shapes our exploration of the solar system, but also strengthens the foundations of humanity's quest for knowledge of the universe. One region that continues to stir intrigue is the Oort cloud. Situated at the very outer edges of our solar system, it represents one of the last great mysteries in our cosmic neighborhood. Thought to be a vast, spherical shell composed of icy objects, the Oort cloud extends nearly 1 light-year from the Sun, an astonishing distance that hints at the magnitude of what lies beyond. Within this remote region, scientists believe there are billions of comets, icy remnants from the early days of the solar system. Despite its potential to unlock vital information about our cosmic origins, the Oort cloud remains largely unexplored. The significance of the Oort cloud goes far beyond its mere existence. It functions as a giant reservoir of comets, which sometimes make their way into the inner solar system. As these comets approach the Sun, they develop bright, shining tails, becoming visible to observers on Earth. Each comet provides a snapshot into the conditions of the early solar system, giving scientists a window into the building blocks that eventually formed the planets. Because the Oort cloud is believed to contain material that has remained largely untouched since the solar system's formation, each comet may hold vital clues about the chemical and elemental conditions that existed billions of years ago. Moreover, the Oort cloud's influence extends beyond just its physical contents. It provides insights into the gravitational dynamics at play within the solar system. While we cannot directly observe the Oort cloud, its presence is inferred by the orbits of long-period comets, which are believed to have originated in this distant region. These comets don't simply wander aimlessly. They are pushed toward the inner solar system by some external force. That force might be the gravity of passing stars or even the gravitational influence of the Milky Way itself. In this way, the Oort cloud offers proof that our solar system is not a self-contained entity, but one that interacts with a broader cosmic environment. As scientists continue to study the Oort cloud, new questions arise. How did this distant region form? What forces determine the orbits of the icy bodies within it? Each new discovery brings with it new mysteries, revealing how much more there is to learn about the history and dynamics of our solar system. By investigating the Oort cloud, researchers are piecing together the story of our cosmic origins and mapping the invisible forces that shape the trajectories of celestial bodies across the universe. One of the most exciting developments in space research is the introduction of phase space mapping. This innovative technique provides a deeper, more nuanced view of the cosmos by representing the states and dynamics of celestial bodies in a multidimensional space. Each point within this framework reflects the position and momentum of an object, not just where it is located, but how it moves and interacts with other objects over time. By applying phase space mapping to our understanding of the universe, we gain insights into the gravitational relationships that define the behavior of entire systems. For example, instead of merely knowing the location of stars, phase space mapping allows us to track their trajectories through the galaxy. This provides a much more dynamic picture of the universe. It reveals how stars, galaxies, and even dark matter interact under the influence of gravity. The technique is a significant leap forward, offering a more holistic view of cosmic structures and revealing insights into the forces shaping their evolution. Beyond its applications to large-scale structures, phase space mapping also opens up the possibility of uncovering hidden patterns and anomalies in cosmic phenomena. It can help astronomers identify unusual interactions between celestial bodies, like the collision of galaxies, the formation of new stars, or the behavior of enigmatic objects like black holes. These discoveries may help us refine our current models and offer new perspectives on the fundamental laws of physics. As technology continues to advance, phase space mapping will undoubtedly uncover new elements of the universe that have previously eluded our detection. With each refinement, we move closer to a richer, more intricate understanding of the cosmos, enabling us to ask even deeper questions about the nature of existence. Interstellar travel, journeying beyond our solar system, represents a bold and tantalizing frontier. The technical hurdles involved in traveling to another star system are immense, but the potential rewards are even greater. The discoveries awaiting humanity in the vastness of interstellar space could redefine everything we know about the universe. Imagine encountering worlds that are radically different from Earth, planets with atmospheres unlike anything we've seen, or star systems with strange and unexpected phenomena. These unexplored realms could hold the key to solving some of the most profound questions about life, the laws of physics, and the nature of the cosmos itself. The journey between stars may one day become the ultimate adventure, offering limitless possibilities for future explorers.